Hello, and welcome to The Sleepy Scientist. This is your quiet corner of the internet, a place where you can let your mind drift, your breathing slow, and the day's edges soften. Before we begin, I'd love to know, where in the world are you listening from tonight? Whether you're curled up in bed, tucked into a couch, or somewhere entirely unexpected, it's wonderful to have you here. If you're new, I'd be grateful if you gave this video a like and subscribed. And to those of you already subscribed, thank you for continuing to join me on these slow, curious journeys. Now, I'll try my best not to make this video so fascinating that you stay up all night, but if it does keep you awake, at least you'll drift off knowing a few more secrets about our world. So, settle in. The sea has been with us for as long as the earth has been blue, and tonight we'll explore its story in all its depth. But here's something to ponder as we begin. If most of our planet is covered by water, why do we still call it Earth? The sea is the largest living system on our planet, and yet it remains the least explored. It is at once ancient and ever-changing, a place where geology, chemistry, physics, and biology swirl together in endless motion. The water you see at the shore today may have carried the breath of a whale in another age, or drifted above volcanic vents deep beneath the Pacific. We'll begin by understanding the sea not as a single entity, but as a collection of worlds. There are waters lit bright by the sun, where plankton bloom in clouds that feed the planet. There are coasts that rise and fall under the pull of the moon, teeming with creatures that cling, burrow and dart. And there are depths so dark and pressurized that no human could survive there unaided, yet life flourishes, thriving without sunlight. As we travel, we'll explore the forces that shape these waters, the tides that tug at continents, the currents that carry heat around the globe, the chemistry that keeps marine life alive. We'll meet the architects of coral cities, the wanderers of the open ocean, and the invisible drifters that quietly produce much of the air we breathe. The ocean is more than a backdrop for life. It is the stage, the script, and the quiet director of Earth's climate and seasons. It has shaped our history, our myths, and our survival. And though it covers more than 2/3 of the planet, we've only glimpsed its surface. By the time we finish, you'll have walked the shores, drifted through the sunlight zones, descended into the midnight depths, and returned with new eyes for the water that touches every part of life. So let's begin, at the very start when the oceans themselves were born. If you could visit Earth more than 4.5 billion years ago, you would not find the calm blue world we know today. Instead, you would step into a place still glowing from its violent birth, with molten rock dominating the surface, and a heavy, toxic atmosphere swirling above. The ground would tremble with constant volcanic activity, the air would sting with gases, and not a single drop of liquid water would greet you. The oceans, so vast and ancient in our minds, had not yet been born. The story of how those oceans arrived is one of science's great detective tales, and while no single theory can yet claim to be the whole truth, there are two leading contenders. One points far beyond our skies to the icy reaches of the solar system. Billions of years ago, the young Earth was under constant bombardment from comets and water-rich asteroids. These cosmic visitors, many formed in the cold outer regions, carried frozen water in their cores. Each time one struck Earth, its ice would instantly vaporize, releasing water into the atmosphere. It may seem far-fetched that impacts could fill an ocean, but remember that this was not a one-off event. The planet endured millions of such collisions over a span of hundreds of millions of years. Slowly, the water delivered by these frozen travellers could have added up to the vast quantities we see today. The second theory keeps the origin story closer to home. Deep within Earth's mantle, water can exist trapped within minerals, locked away in chemical bonds. In the planet's earliest days, volcanic eruptions were constant and unimaginably powerful. Alongside molten rock, these eruptions vented enormous amounts of gas, including water vapour. As the surface cooled, this vapour condensed into rain. And not a gentle drizzle, This would have been an epic downpour lasting thousands of years. The skies would have been dark and turbulent, lightning flashing constantly as torrents of water fell, pooling in lowlands and craters until they merged into the first seas. Many scientists suspect that the truth lies in a combination of the two ideas. Water delivered from the depths of the planet through volcanism, supplemented by water from countless icy impacts. However it happened, once liquid water covered the Earth, everything changed. The planet now had a powerful heat regulator, as water absorbs and releases heat slowly. It had a medium in which chemical reactions could take place more easily, and most importantly, it had a potential cradle for life. Those earliest oceans were nothing like the ones we know now. The water was likely cloudy, filled with dissolved minerals and metals leached from the young crust. Oxygen was scarce or entirely absent, replaced by gases like carbon dioxide, methane and ammonia. The colour might have been greenish or even reddish, depending on the minerals in suspension. The moon, newly formed from a massive collision, was far closer than it is today, tugging at the seas with powerful tides that would have been far more extreme than we experience now. It was in these alien seas that life may have begun. One possibility is that it started in shallow coastal waters, where the warmth of the sun and the gentle concentration of organic molecules created the right conditions for chemistry to become biology. Another possibility is the deep ocean, at hydrothermal vents, where mineral-rich water gushes from the seafloor, providing both heat and energy. Here, in darkness and under immense pressure, simple molecules could have assembled into more complex structures, eventually giving rise to the first living cells. By around 3.5 billion years ago, the oceans were no longer empty. They were home to microscopic organisms, the earliest life forms on Earth. These single-celled pioneers were incredibly resilient, able to survive in conditions that would kill most modern species. Some of them developed a revolutionary talent: photosynthesis. Using sunlight, carbon dioxide and water, they created sugars for energy and released oxygen as a byproduct. At first, this oxygen reacted with minerals in the oceans, slowly altering their chemistry. But over millions of years, it began to accumulate in the atmosphere in what scientists call the Great Oxidation Event. This transformation set the stage for more complex life. The chemistry of the oceans shifted toward the oxygen-rich balance we know today, and entirely new types of organisms evolved to take advantage of it. The seas became not just the birthplace of life, but also its great engine, driving biological innovation for billions of years. If we could compare the ancient oceans to the modern ones, the differences would be striking. Today's oceans are relatively stable in temperature, salinity, and oxygen content, supporting an astonishing diversity of life. The blue colour we see from space comes from the way water absorbs and scatters light, something that would not have been so vivid in the mineral-rich seas of the past. Modern currents distribute heat and nutrients around the globe, while in the early oceans, circulation patterns may have been sluggish and patchy. And yet, despite the changes, there is a deep continuity. The water lapping at the shore today contains molecules that have been part of the ocean for billions of years, cycling endlessly through evaporation, precipitation, and flow. Some of the very same water that splashed against volcanic islands in Earth's youth now drifts in currents beneath the polar ice or swirls in warm tropical shallows. It is humbling to think that every drop holds a history stretching back to a time before there were continents, before there was oxygen in the air, before there was even life to notice it. The birth of the oceans was not just the beginning of a geological feature, it was the starting point for the entire story of life on our planet. Without them, there would be no forests or deserts, no animals or humans, and perhaps no Earth as we know it at all. If the oceans could be drained like an oversized bathtub, the landscape beneath would surprise you. Far from being flat and featureless, the seafloor is a world of towering ridges, vast plains, deep trenches, and hidden volcanoes. It is as dramatic as any terrain above water, but cloaked in darkness and mystery. This hidden geography is what gives the sea its shape, dictating where it is shallow, where it plunges to impossible depths, and how life and currents move through it. The largest features of this world are the ocean basins, immense depressions in the Earth's crust that hold the planet's water. These basins exist because the crust is not a single solid shell, but a mosaic of massive tectonic plates. These plates float atop the hot, slowly flowing mantle, shifting over millions of years. Where they move apart, new crust is born as molten rock rises from below, forming underwater mountain ranges called mid-ocean ridges. The Mid-Atlantic Ridge, for example, snakes for thousands of kilometers down the center of the Atlantic Ocean, constantly creating new seafloor and slowly pushing the continents apart. Where plates collide, the story is different. One plate may slide beneath another in a process called subduction, forcing parts of the seafloor deep into the mantle. These subduction zones are home to the deepest trenches on Earth. The Mariana Trench in the Western Pacific is the most famous and the deepest, plunging to more than 11,000 meters. If Mount Everest were placed inside it, the mountain's summit would still be over 2 kilometers below the surface. Not all of the seafloor lies in such abyssal depths. Along the edges of the continent stretch the continental shelves, broad, shallow extensions of land submerged under relatively little water, often less than 200 meters deep. These shelves slope gently until they reach the continental slope, where the seafloor drops sharply into the deep ocean basins. Continental shelves are some of the most biologically productive places on Earth, thanks to sunlight penetration and the constant stirring of nutrient-rich waters. Coastal cities, fisheries, and shipping lanes all depend on them, making them as important to human life as they are to marine ecosystems. The depth of any given sea depends on a combination of geology, plate activity, and sediment buildup. Some seas, like the North Sea or the Persian Gulf, are shallow because they rest on continental shelves. Others, like the Caribbean Sea, are much deeper because they occupy parts of oceanic crust formed far from land. Sediment carried by rivers and wind can slowly fill in shallower basins, while tectonic stretching or subduction can create deeper ones. This is why the shape of the sea is constantly changing over geological time, even if it seems eternal from our human perspective. Although we speak of the ocean as one vast body of water, it is divided into 5 major oceans, each with its own character. The Pacific Ocean is the largest, covering more area than all the continents combined. It contains the deepest point on Earth, the Mariana Trench, and thousands of islands scattered like green jewels. Its ring of fire is a chain of volcanic and seismic activity that traces the outlines of its restless tectonic boundaries. The Atlantic Ocean is smaller but still immense, stretching between the Americas to the west and Europe and Africa to the east. Its most striking feature is the Mid-Atlantic Ridge, which runs like a spine down its centre, slowly widening the basin as magma emerges and cools. The Atlantic also carries one of the most famous currents, the Gulf Stream, which transports warm water from the tropics toward Europe, influencing climates far from its shores. South of these lies the Southern Ocean, encircling Antarctica in a continuous, unbroken ring. Its defining feature is the Antarctic Circumpolar Current, the most powerful ocean current on Earth, which connects the Atlantic, Pacific, and Indian Oceans and helps regulate global climate. The waters here are cold and often turbulent, but they are also incredibly rich in life, supporting vast populations of krill, whales, and seabirds. The Indian Ocean, bordered by Africa, Asia, and Australia, is the warmest of the 5. Monsoon winds have shaped human history here for thousands of years, carrying traders and explorers across its waters. It is dotted with small island nations and coral reefs, and its warm currents play a vital role in regulating rainfall across large parts of Asia and Africa. Finally, the Arctic Ocean is the smallest and shallowest of the 5, much of it covered by sea ice for most of the year. It is a unique environment where freezing temperatures, seasonal extremes of light and darkness, and the mixing of Atlantic and Pacific waters create a delicate but rich ecosystem. Though these oceans are named separately, the reality is that they are connected. Water flows freely between them, moving heat, nutrients, and life around the globe. The boundaries are human creations, useful for navigation and study, but the sea itself is a single, continuous body. The shape of its basins and the position of its shelves and ridges dictate the patterns of currents, the distribution of marine habitats, and the rhythms of climate. Beneath the waves lies a world every bit as complex as the one we see on land, a hidden architecture that has guided the course of life and the history of our planet for billions of years. The oceans may seem unchanging from day to day, but their foundations are in slow, constant motion, sculpting the face of the earth in ways we're only beginning to fully understand. Stand on a beach long enough and you will notice something curious. The waterline creeps forward, swallowing patches of sand and pebbles, and then, hours later, it slips back, revealing them once again. This steady advance and retreat is the tide, one of the most reliable and ancient rhythms on Earth. It is not a trick of the wind or a quirk of the waves. It is the pull of celestial bodies written directly onto the surface of the sea. The moon is the main choreographer of this movement. Its gravity tugs on the Earth, pulling the oceans slightly toward it. Because water flows freely compared to solid ground, it responds to this pull by forming a bulge on the side of the planet facing the moon. But gravity has a partner in this dance: inertia. As Earth and Moon orbit a common centre of mass, the water on the far side of the planet experiences a sort of outward fling, creating a second bulge. These twin swells of water remain roughly aligned with the Moon, and as the Earth rotates, any given location passes through them twice each day, producing 2 high tides and 2 low tides in a cycle of about 24 hours and 50 minutes. The Sun also plays a role in shaping tides. Its gravitational pull is weaker than the Moon's when it comes to our oceans, but it is far from negligible. When the Sun, Moon and Earth line up, during new moons and full moons, their combined forces create higher than average tides, known as spring tides. These are not named for the season, but for the way the water seems to spring higher. In contrast, when the Sun and Moon are at right angles to each other relative to Earth, during the first and third quarters of the Moon, their gravitational pulls partially cancel out, producing gentler changes in water level called neap tides. The difference between spring and neap tides can be dramatic, especially in places with large tidal ranges. The Bay of Fundy in Canada, for instance, can experience tidal changes of over 15 metres between high and low water. In other places, the change may be less than a metre. Local geography, ocean depth, and coastline shape all influence how the tidal forces are expressed. Narrow bays can amplify the movement of water, while wide, open coasts might see more modest changes. Tides are far more than a simple up and down motion. They are vital to the functioning of many marine and coastal ecosystems. In intertidal zones, the stretch of shore between the highest and lowest tide marks, life is adapted to constant change. Barnacles cling tightly to rocks, sealing themselves in when the water leaves them high and dry. Seaweeds anchor firmly, swaying with the waves when submerged and lying flat and damp when exposed. Crabs, snails, and small fish move with the water, making use of pools and crevices to survive the hours out of the tide's reach. Estuaries, where rivers meet the sea, depend on tides to bring in fresh supplies of nutrients and to flush away waste. These nutrient pulses feed plankton, which in turn support fish, birds, and marine mammals. Coral reefs too rely on tidal currents to carry away debris and deliver plankton-rich water to the hungry mouths of corals and filter feeders. Even far offshore, in places where the tidal range at the surface might seem small, the vertical movement of water can stir deeper layers, redistributing nutrients and oxygen through the water column. Humans have long lived by the rhythm of the tides. Fishermen plan their work to match the ebb and flow, knowing that certain species are easier to catch at specific stages. Sailors have navigated with tidal charts for centuries, timing departures and arrivals to ride favourable currents. In some parts of the world, tidal mills once harnessed this energy to grind grain, and today, engineers are developing tidal power systems to generate clean electricity from the steady, predictable movement of water. Tides also hold cultural significance. In many coastal communities, they have shaped myths, rituals, and traditions. The pull of the moon on the sea has inspired poetry, music, and folklore, often linked to the cycles of growth, change, and renewal. For some, the tide's rise and fall is a reminder of nature's constancy. For others, it is a symbol of impermanence. Despite their reliability, tides are not identical every day. Subtle changes in the moon's distance from Earth, the tilt of the planet's axis, and seasonal weather patterns can all influence their timing and strength. Storms can amplify high tides, causing dangerous surges, while high-pressure systems can suppress them slightly. Over geological timescales, the tides themselves change shape as the continents drift and ocean basins shift. The relationship between tides, the moon, and the sun is one of the most elegant examples of celestial mechanics influencing everyday life. You can see it in the exposed rocks where seaweed clings, in the shifting sandbars, and in the wayboats in a harbour rest low in the water 1 hour and float high the next. The gravitational conversation between Earth and its companions plays out endlessly, pulling at the sea and setting the tempo for countless forms of life. Every incoming tide carries the ocean closer to the land, and every outgoing tide pulls it back toward the deep. It is a pulse that has never missed a beat in billions of years, a link between the motion of the heavens and the restless breathing of the sea. If you have ever watched a river flow, you already have some idea of what ocean currents are like, except that the rivers in the sea can be thousands of kilometres wide, hundreds of metres deep, and can carry more water in a single second than all the world's rivers combined. These immense, steady movements of water are the arteries of the ocean, connecting distant regions, distributing heat, and shaping life and climate across the planet. Surface currents are the most immediate part of this system, although they are not something you can see just by looking out from the shore. They are driven mainly by winds, which push against the ocean's surface. Over time, the friction between air and water sets the upper layers moving. Because Earth is spinning, these flows are deflected to the right in the northern hemisphere and to the left in the southern hemisphere by the Coriolis effect. The result is the formation of vast circular systems called gyres, which dominate the surface circulation of each major ocean basin. In the North Atlantic, for example, winds and the Coriolis effect combine to create a clockwise gyre. In the North Pacific, the same forces produce a similar pattern. In the southern hemisphere, gyres spin the other way, circling counterclockwise. These gyres do more than simply move water around. They carry heat, salt, nutrients, and even drifting marine life from one part of the world to another. Beneath the surface, another kind of current flows, slower, deeper, and far more extensive. This is the thermohaline circulation, often called the ocean conveyor belt. It is driven not by wind, but by differences in temperature and salinity, which together determine the density of seawater. Cold, salty water is denser and sinks, while warmer, fresher water is lighter and rises. In the North Atlantic, surface water cools and becomes saltier as sea ice forms, then sinks into the depths, beginning a journey that can last centuries as it flows southward through the Southern Ocean into the Pacific and Indian Oceans, and eventually rises again in distant upwelling zones. This circulation is one of the main reasons Earth's climate is as stable as it is. Without it, the tropics would become unbearably hot, while the polar regions would grow even colder. The conveyor belt moves vast amounts of heat from the equator toward the poles, moderating temperatures and influencing weather patterns far from the ocean itself. Monsoon rains in Asia, droughts in Africa, and storm tracks in the Atlantic can all be shaped by shifts in this circulation. The Gulf Stream is perhaps the most famous surface current in the world. It begins in the warm waters of the Gulf of Mexico, flows up the eastern coast of the United States, and then sweeps out into the Atlantic toward Europe. This ribbon of warm water helps keep Western Europe's climate milder than other regions at similar latitudes. Without it, winters in places like London might resemble those in northern Canada. The Gulf Stream is not just a single flow, but part of a complex network of currents that interact with winds, tides, and the shape of the seafloor. Other notable currents include the Kuroshio Current, which carries warm tropical water northward along the coast of Japan, the California Current, which flows southward along the western United States, bringing cool, nutrient-rich water that supports thriving fisheries, and the Humboldt Current off South America, famous for its rich upwelling zones that feed immense populations of anchovies, seabirds, and marine mammals. The Antarctic Circumpolar Current, the largest of all, circles Antarctica uninterrupted by any landmass, connecting the waters of the Atlantic, Pacific, and Indian Oceans, and helping to drive the global conveyor belt. Currents do not just move water, they move life. Many marine species depend on currents to carry their larvae to suitable habitats. Sea turtles, jellyfish, and planktonic organisms drift on them, sometimes travelling vast distances without any active swimming. Migrating whales and fish often follow predictable current routes, which can offer both navigation cues and access to feeding grounds. In places where currents bring deep, nutrient-rich water to the surface, enormous blooms of phytoplankton appear, feeding entire food chains from tiny crustaceans to the largest whales. For humans, currents have always been both a challenge and an advantage. Ancient mariners learned to use them for faster travel, following seasonal winds and steady flows to cross oceans. Modern shipping routes are still planned with currents in mind to save time and fuel. Fishermen know that productive waters are often linked to upwelling zones, where cold, nutrient-filled water from the depths rises to meet the sunlight. Even recreational sailors and surfers feel their influence, whether riding a favourable stream or contending with a stubborn countercurrent. Currents can also concentrate less welcome passengers. Floating debris, including plastic waste, can become trapped in the calm centres of gyres, forming large accumulation zones such as the Great Pacific Garbage Patch. These areas are a stark reminder that the ocean's circulation does not distinguish between plankton and plastic. Whatever floats can travel the same routes as living things. Changes in major currents can have dramatic consequences. During El Niño events, for instance, the weakening of trade winds in the Pacific alters the normal current patterns, reducing upwelling off the coast of South America and causing warm water to pool in the central and eastern Pacific. This disrupts weather worldwide, triggering droughts, floods, and shifts in storm activity. On a longer timescale, scientists are closely watching signs of potential slowdown in the Atlantic's thermohaline circulation due to the melting of polar ice and the influx of fresh water, which could have far-reaching effects on global climate. Whether swift or slow, shallow or deep, ocean currents are the great connectors of the planet's water. They tie distant coasts together, carry the seeds of life across vast distances, and quietly influence the air we breathe and the weather we experience. The sea may seem boundless and chaotic, but beneath its shifting surface lies a circulation system as intricate and vital as any heartbeat, steady, far-reaching, and essential to life on Earth. Stand beside the sea for even a short while, and you will notice it never truly rests. Water rises and falls in graceful arcs, endlessly folding in on itself. This is the ocean's heartbeat. Waves. They can be tiny ripples that barely disturb the surface or towering walls of water that carry immense energy. No matter their size, all waves begin as the transfer of energy, and most start with something as simple as the wind. When wind blows across the surface of the water, friction between the air and the sea transfers energy from the moving air into the water below. The first effect is the creation of small ripples known as capillary waves. These tiny ridges increase the surface area for the wind to push against, allowing the energy transfer to grow more efficient. The longer the wind blows, the stronger it is, and the greater the distance it travels over open water, known as the fetch, the larger the waves it can generate. That is why a strong wind on a small lake might raise only modest chop, while the same wind blowing for days across thousands of kilometers of open ocean can produce swells many meters high. It is important to note that in most cases the water itself is not travelling forward in great sweeping motions. Instead, the energy moves through the water, causing the water particles to move in small circular orbits. As a wave passes, the particles return to almost the same place they started. If you were to watch a drifting piece of seaweed far from shore, you would see it rise and fall with the waves, but not necessarily travel much distance unless pushed by a current or wind-driven surface drift. Not all waves are created by the wind. Some of the most dramatic are tsunamis, which have entirely different origins. Tsunamis are usually triggered by powerful underwater disturbances such as earthquakes, volcanic eruptions, or landslides. These events suddenly displace huge volumes of water, sending out waves that can travel across entire ocean basins. In the deep ocean, a tsunami may be barely noticeable at the surface, its wave height often less than a meter, but it can travel at speeds approaching those of a passenger jet. As it approaches shallow coastal waters, the wave slows down and the water piles up, sometimes reaching heights of 10 meters or more. The arrival of a tsunami is often preceded by a sudden eerie retreat of the sea from the shoreline, a phenomenon that can serve as a natural warning for those who recognize it. Storm surges are another type of exceptional wave event, though they are different from tsunamis. They occur when powerful winds from storms, especially hurricanes and typhoons, push seawater toward the coast. Combined with low atmospheric pressure, this creates a bulge of water that can flood large areas of land. While storm surges are caused by weather systems rather than seismic activity, they can be just as destructive to coastal communities. For most of the world's shorelines, most of the time, waves are gentler, shaped by winds far away from where they eventually arrive. Large, smooth swells often form in the open ocean after storms have passed. These swells can travel for thousands of kilometers, their energy spreading out and their shapes smoothing into regular rolling patterns. When they finally meet land, they transform into the breakers we know so well. The transformation happens because the lower part of the wave begins to interact with the seafloor. As the depth decreases to about half the wavelength of the wave, the orbital motion of water particles is disrupted. Friction with the bottom slows the base of the wave, but the crest continues moving at its original speed. This causes the wave to steepen until it becomes unstable and topples forward. The result is a breaker, a tumbling, foamy display of energy meeting resistance. The type of breaker depends largely on the slope of the shoreline and the wave's energy. On steeply sloped beaches, waves may plunge dramatically, curling into hollow tubes before crashing down. These plunging waves are a favourite of surfers who ride the pocket of air inside the curl. On gently sloping beaches, waves tend to spill gradually, their crests tumbling over in a more subdued fashion. Somewhere in between, you find surging breakers, which rise sharply but collapse onto the shore without fully curling. The rhythm of waves is one of the most hypnotic sounds in nature. It is steady yet never perfectly predictable, varying subtly with each set. Many people find themselves unconsciously matching their breathing to the pace of incoming and outgoing surf. This rhythm is more than a human comfort. It shapes coastlines over time. Waves erode cliffs, move sand along shores, and create features like sandbars and spits. They are both sculptor and caretaker of the boundary between land and sea. For marine life, waves bring constant change. In the surf zone, organisms must withstand the push and pull of moving water. Crabs burrow quickly between waves, clams anchor themselves deep in the sand, and certain fish are streamlined to dart through the turbulence. Even offshore, the mixing caused by waves helps distribute oxygen and nutrients in the upper layers, fueling plankton blooms that support entire ecosystems. The relationship between waves and humans is a long one. For as long as we have sailed, we have learned to read the patterns on the water to predict weather and find the most efficient routes. Fishermen have used the surf's behaviour to decide where to launch and land their boats. Coastal communities have lived in respect of the power that waves can wield during storms, even as they enjoy the bounty and beauty of calmer days. Whether they arrive as a faint ripple brushing your feet or as towering swells that pound the cliffs, waves are a reminder that the ocean is never truly at rest. They carry the signatures of distant winds and deep forces, linking places separated by vast stretches of sea. Their constant motion is the ocean's own pulse, ancient, enduring, and endlessly varied. If you could take all the salt out of the ocean and spread it evenly across Earth's surface, you would end up with a layer more than 40 meters deep. That is a staggering amount of seasoning, and it is one of the defining features of our planet's seas. But how did the ocean get so salty, and why does it stay that way? The story of salt begins on land. Rainwater, though it looks pure, is slightly acidic because it absorbs carbon dioxide from the atmosphere, forming a weak carbonic acid. As this rain falls on rocks, it slowly breaks them down through weathering. The process releases minerals, including sodium and chloride, the two main ingredients of common table salt, along with a variety of other ions such as magnesium, calcium, potassium and sulfate. Rivers carry this mineral mix into lakes and eventually into the sea. In a closed lake without an outlet, the salt can build up quickly, creating places like the Dead Sea. In the global ocean, the process happens over geological timescales, but the result is the same, a gradual accumulation of salts in the water. Unlike rivers or lakes, the oceans have no true drain. Water leaves mainly through evaporation or freezing, but the salts remain behind. Over millions of years, this has allowed the ocean's salinity to stabilise at an average of about 35 parts per thousand, roughly 3.5% by weight. That means every litre of seawater contains about 35 grams of dissolved salts, most of it sodium chloride. However, not every part of the ocean is equally salty. Salinity can vary depending on climate, geography and ocean currents. Near the mouths of large rivers like the Amazon, freshwater influx dilutes the seawater, creating zones with lower salinity. Polar regions also tend to have lower salinity, because melting ice adds fresh water to the mix. Conversely, in hot, dry areas like the Red Sea or the Persian Gulf, high evaporation rates leave the remaining water saltier than average. These differences might seem small, perhaps only a few parts per thousand, but to marine life, they can mean the difference between survival and stress. Organisms in the sea are adapted to specific salinity ranges. Some, like many coastal fish and estuarine species, are euryhaline, meaning they can tolerate a wide range of salt concentrations. Salmon, for example, are born in fresh water, migrate to the salty ocean, and return to rivers to spawn. Others, like most open ocean fish and corals, are stenohaline, meaning they can survive only within a narrow salinity range. Sudden changes in salinity, such as heavy rainfall over a coral reef or an influx of melting ice, can be harmful or even deadly to these sensitive creatures. Salt is only part of the chemical story of seawater. Dissolved gases also play a crucial role in making the ocean habitable. Oxygen, for instance, enters the sea from the atmosphere and through the photosynthesis of marine plants and phytoplankton. While the surface layers are usually rich in oxygen, deeper waters can be depleted, especially in areas with poor circulation. Carbon dioxide is also abundant in seawater, far more so than in the atmosphere, because it reacts with water to form bicarbonate and carbonate ions. These forms of carbon are essential to marine life, providing the building blocks for shells and skeletons in corals, mollusks, and many plankton species. Nutrients dissolved in seawater, including nitrogen, phosphorus, and silica, are the ocean's version of fertilizer. They are vital for phytoplankton growth, which in turn supports the entire marine food web. These nutrients enter the ocean mainly through river runoff, decomposition of organic matter, and upwelling currents that bring nutrient-rich deep water to the surface. Too many nutrients, however, can cause problems, fueling algal blooms that deplete oxygen and create dead zones where little can survive. Another key factor in the chemistry of seawater is its pH, a measure of how acidic or alkaline it is. On average, seawater has a pH of about 8.1, making it slightly alkaline. This stability is largely thanks to the carbonate buffering system, which resists sudden changes in acidity. However, human-driven increases in atmospheric carbon dioxide are altering this balance. As more carbon dioxide dissolves into the ocean, it forms carbonic acid, lowering the pH in a process known as ocean acidification. Even small shifts in pH can affect marine organisms, particularly those that build shells or skeletons from calcium carbonate. Corals, oysters, and certain plankton species are especially vulnerable, as more acidic conditions make it harder for them to form and maintain their structures. Seawater's chemical composition is remarkably consistent across the globe, even if salinity levels vary. The proportions of major ions, sodium, chloride, magnesium sulfate, calcium and potassium, remain in roughly the same ratios whether you're in the Arctic Ocean or the middle of the Pacific. This consistency is known as the principle of constant proportions, and it means that by measuring just one major ion, scientists can estimate the concentrations of all the others. While salt is the most noticeable feature, it is the combination of salts, gases, nutrients and pH balance that makes the ocean a suitable home for life. It is a delicate mix maintained by natural cycles over millions of years. Yet it is also a system under pressure from human activity, from nutrient runoff and pollution to rising carbon dioxide levels. Understanding the chemistry of salt water is not just a matter of curiosity, it is essential for protecting the health of the ocean and the countless species, including ourselves, that depend on it. The sea's saltiness connects us to the deep history of our planet. It is the taste of ancient rains and rivers, of minerals worn from stone over eons, of a world in constant motion. Every drop of seawater carries the imprint of that long journey, a reminder that the ocean is not simply a body of water, but a living, breathing chemical engine that sustains life on Earth. If you were to float gently at the very top of the ocean and look downward, you would be gazing into the epipelagic zone, the sunlit realm of the sea. This is the ocean's upper skin, extending from the surface down to about 200 meters, where sunlight still penetrates enough to power photosynthesis. It is bright, comparatively warm, and alive with movement. This is where much of the ocean's visible action happens, where light and life meet in a swirling, shimmering partnership. The epipelagic zone is sometimes called the photic zone, from the Greek word for light, and it is here that the ocean's great energy engine begins. Sunlight fuels the tiny green and golden powerhouses of the sea, the phytoplankton. These microscopic plants and plant-like algae use sunlight, water and carbon dioxide to produce food through photosynthesis. In doing so, they generate roughly half of the world's oxygen, meaning every second breath you take has passed through a plankton's chloroplast. While each plankton cell is small enough to slip through a fine mesh, together they create vast blooms visible from space, painting the sea in swirls of green or turquoise. Plankton form the very base of the marine food web. They're eaten by zooplankton, tiny drifting animals like copepods and krill, which in turn are eaten by fish, squid, and countless other creatures. Even the largest animal on Earth, the blue whale, ultimately depends on these minute organisms, straining massive mouthfuls of krill and plankton-rich water through its baleen plates. Remove plankton, and the ocean's entire food chain would collapse. It is a humbling thought that such a delicate foundation supports the vast diversity of ocean life. Light in the epipelagic zone is not uniform. Sunlight is scattered and absorbed as it travels through water, and different wavelengths behave differently. Red light disappears first, fading within just a few meters, which is why deep water looks blue. Those longer wavelengths simply cannot make it far. Blue and green penetrate the deepest, giving the open ocean its characteristic colour. For animals that live here, this light environment shapes everything from their vision to their camouflage. Many fish in the epipelagic zone are countershaded, darker on top to blend with the dim water below when seen from above, and lighter on the bottom to match the bright surface when seen from below. Others are silvery and reflective, making them nearly invisible in the shifting light. Predators have evolved eyes tuned to detect movement in these conditions, while prey species rely on speed, schooling, and stealth to avoid being spotted. The clarity of the water also influences how far predators can see. In tropical waters, where plankton densities are low and water is clearer, vision can extend tens of meters. In more productive plankton-rich waters, visibility might be just a few meters, creating a different hunting and hiding dynamic. For fast-swimming predators like tuna, swordfish, and mahi-mahi, sight is critical, and their eyes are adapted to make the most of the available light. Among the most enchanting residents of the epipelagic zone are the jellyfish. These drifting, gelatinous creatures have no brains, no bones, and in many cases no real control over their movement. They pulse slowly through the water, going where the currents take them, feeding on plankton and small fish. Some species are almost transparent, others are vividly coloured, and a few possess tentacles that trail many meters behind them. Despite their delicate appearance, jellyfish are ancient survivors, having drifted through Earth's seas for more than 500 million years. Then there are the sleek, powerful hunters like tuna. Built for speed, with streamlined bodies and strong tails, tuna are among the fastest fish in the sea. They travel in schools, sometimes covering thousands of kilometers in search of food, and their warm-blooded physiology gives them a predatory edge in cooler waters. Their sharp eyesight and coordination make them formidable in the chase, especially when they herd schools of smaller fish toward the surface. Dolphins, too, are a familiar sight in the epipelagic zone. Social, intelligent, and playful, they often work together to corral fish, using clicks and whistles to communicate. While dolphins are mammals needing to surface for air, they are perfectly at home in this sunlit expanse, riding the bow waves of ships or leaping in graceful arcs. Their streamlined shapes and cooperative hunting techniques have made them one of the ocean's most successful and well-known predators. Of course, the epipelagic zone is not all predators and prey locked in constant pursuit. It is also a place of great seasonal and geographical variation. In some regions, nutrient-rich waters well up from below, feeding massive plankton blooms that support thriving fisheries. In other areas, like the central gyres of the oceans, nutrients are scarce and life is more sparsely distributed. These differences shape the communities that form here, from teeming shoals of sardines to scattered wanderers like ocean sunfish. The interplay of sunlight, chemistry, and biology in the epipelagic zone is one of Earth's great balancing acts. Here, the simple act of a plankton cell splitting into two, or a jellyfish pulsing slowly through the water, is part of a vast interconnected system. Energy from the sun flows into the plankton, into the zooplankton, into the fish, into the dolphins, and eventually into us. The food on our plates and the oxygen in our lungs are tied, in ways we rarely think about, to this luminous living layer of the sea. Even the calmest day at sea is alive with countless invisible dramas in this zone. A tuna's chase, a copepod's feeding, a plankton bloom stretching across hundreds of kilometers. They all happen against the glittering backdrop of the ocean's surface. The epipelagic zone is, in a way, the ocean's face to the world, the place where it breathes, feeds, and greets the sunlight. And while it is only a thin slice of the ocean's vast depth, it is one of the most crucial and breathtaking layers of life on Earth. The coastal edge is where the ocean meets the land, a shifting, breathing boundary that is never quite the same from one moment to the next. It is a place of contrasts, both harsh and gentle, calm and violent, stable and constantly changing. For all the power and mystery of the open ocean, it is often here, in these shallows and shorelines, that life is at its most diverse and densely packed. The meeting of sea and land creates one of Earth's richest environments, and yet it is also among the most challenging places to live. One of the most fascinating parts of the coastal edge is the intertidal zone, the strip of land that is alternately covered and uncovered by the tides. Twice a day the tide comes in and submerges it completely. Twice a day it retreats and leaves it exposed to the air. To survive here is to endure extremes, immersion in salt water, exposure to sun and wind, pounding waves, and shifting salinity as rainwater or rivers mix with the sea. For many species, the solution is clever adaptation. Barnacles cement themselves to rocks and close tight when the tide goes out, trapping moisture inside. Mussels cluster together, holding fast with their tough abyssal threads, while sea stars creep across the rocks to hunt for food in tide pools. Tide pools themselves are miniature worlds, pockets of seawater left behind in rocky hollows when the tide retreats. In these small basins, anemones sway, tiny fish dart between shadows, and hermit crabs scuttle about in borrowed shells. These habitats are highly changeable, one moment calm and glassy, the next churned up by waves. But life here is resilient. Every tide brings the possibility of new food and new dangers, making this zone a place of constant opportunity and constant risk. Moving further along the coastline, we encounter ecosystems that act as buffers between land and sea: mangroves, estuaries, and salt marshes. Each of these is a kind of biological filter, shelter, and nursery rolled into one. Mangroves are remarkable trees that grow in salty tidal waters, their tangled roots arching above the surface like natural sculptures. These roots do more than anchor the trees. They also trap sediment, protect shorelines from erosion, and provide a maze of hiding places for young fish, crabs, and shrimp. In many tropical and subtropical regions, mangroves are the first line of defense against storms, breaking the force of waves before they reach inland communities. Despite their tough, salt-resistant nature, mangroves are vulnerable to coastal development, and their loss can have far-reaching impacts on both marine life and human safety. Estuaries are where rivers meet the sea, creating brackish water, a mix of fresh and salt that shifts with the tides. These nutrient-rich environments are among the most productive on Earth. Riverborne sediments feed blooms of plankton, which in turn attract fish, birds, and countless invertebrates. Estuaries often serve as nurseries for fish and shellfish that later move into the open ocean, making them vital to both natural ecosystems and human fisheries. The constant mixing of salt and fresh water creates unique challenges for organisms that live here, requiring them to handle rapid changes in salinity. Salt marshes, found in temperate regions, are flat, grassy wetlands that flood and drain with the tides. Their tall grasses and sedges slow water flow, allowing sediments to settle and nutrients to build up. This not only creates fertile ground for plants and animals, but also acts as a natural defense against storm surges. Marshes absorb excess water, helping to protect inland areas from flooding, and their dense plant life captures carbon from the atmosphere, making them important allies in climate regulation. Beyond their ecological richness, coastal edges have always been central to human life. Long before cities and ports, early humans were drawn to coasts for their abundance of food and access to trade routes. Shellfish, fish, and seaweed provided sustenance, while the sea itself was a highway for exploration and exchange. Even today, a large proportion of the world population lives within a short distance of the coast, relying on it for food, commerce, and recreation. But living along the coastal edge comes with its own set of risks. Storms, erosion, flooding, and rising seas are all challenges that coastal communities must face. In some areas, the shoreline is retreating year by year as waves and currents reshape the land. Human activity, from dredging to construction to pollution, can accelerate these changes, making coastlines more vulnerable. Balancing the benefits of coastal living with the need to protect these environments is an ongoing challenge for societies around the world. The beauty of the coastal edge lies in its constant change. No 2 days are the same. Tides rise and fall, storms reshape beaches, and new patterns of life emerge with the seasons. For wildlife, it is a place that demands adaptability and resilience. For humans, it is a source of both livelihood and inspiration. Standing at the shoreline, feeling the pull of the tide and the salt-laden wind, one is reminded that this narrow strip is more than just the boundary of the sea. It is a meeting place, a cradle of life, and a vital thread in the fabric of our planet. If the ocean were a city, coral reefs would be its bustling downtown districts, full of life, colour, and intricate architecture. From above, they might look like pale streaks or dark patches beneath the water's surface, but closer inspection reveals sprawling underwater metropolises that support an astonishing array of creatures. These reefs are some of the most productive ecosystems on Earth, rivaled only by rainforests and biodiversity. A coral reef is built from countless tiny animals called coral polyps. Each polyp is a soft-bodied creature related to sea anemones and jellyfish, and like them, it has a ring of tentacles surrounding a central mouth. What makes corals special is their ability to secrete calcium carbonate, the same material found in seashells. Over time, layer upon layer of this hard skeleton accumulates, forming the stony framework of the reef. The living polyps sit on top of the structures left behind by their ancestors, adding to the reef's height and complexity year by year. What is perhaps most extraordinary is that these reefs grow in waters that are often low in nutrients, places where, in theory, there should not be enough food to support such abundance. The secret lies in a remarkable partnership between the coral polyps and microscopic algae called zooxanthellae. These algae live inside the coral's tissues, protected from predators and given access to sunlight filtering through the clear tropical waters. In return, they perform photosynthesis, producing sugars that feed the coral. In fact, most of the coral's energy comes from these symbiotic algae, while the rest comes from catching plankton and tiny organisms drifting in the water. This symbiosis does more than just sustain individual corals, it drives the growth of the entire reef. Because the algae need sunlight, reefs thrive in shallow sunlit waters, usually no deeper than about 30 meters. Here, light fuels photosynthesis, which in turn fuels coral growth, and coral growth creates the structures that provide shelter and feeding grounds for a dazzling array of marine species. A mature reef can support thousands of species. Fish of every shape and colour dart between coral branches, parrotfish scrape algae from the surface, damselfish defend their tiny territories, and clownfish hover protectively near anemones. Crustaceans like shrimp and crabs scuttle through crevices, while octopuses lurk in rocky holes, changing colour to blend with their surroundings. Sea turtles may glide gracefully over the reef, stopping to nibble on sponges while reef sharks patrol the deeper edges. Even the less glamorous inhabitants, worms, sponges, sea cucumbers, play essential roles in keeping the reef ecosystem balanced. The importance of coral reefs extends far beyond their borders. They act as nurseries for countless fish species, many of which later migrate to deeper waters. They provide food for millions of people around the world and support fishing industries both small and large. Reefs also act as natural barriers, breaking the force of waves and protecting shorelines from erosion and storm damage. In places where reefs are healthy, they can reduce the height and energy of incoming waves by more than 90%, saving communities from potentially devastating floods. But for all their resilience in the face of natural challenges, coral reefs are increasingly under threat from human activity. One of the most well-known dangers is coral bleaching, a process that occurs when corals become stressed, often due to rising sea temperatures. Under stress, corals expel the zooxanthellae that live within them. Without these algae, the coral loses its primary food source and its colour, turning ghostly white. If the stress is temporary and conditions improve, the algae can return and the coral can recover. If not, the coral will eventually die. Warmer ocean temperatures are not the only problem. Ocean acidification, caused by the absorption of excess carbon dioxide from the atmosphere, makes it harder for corals to build their calcium carbonate skeletons. Pollution, particularly from agricultural runoff, can smother reefs in sediment or fuel algal blooms that block sunlight. Overfishing disrupts the balance of reef ecosystems, removing key species that help control algae growth. Physical destruction from coastal development, anchor damage, and destructive fishing practices such as blast fishing further erodes reef health. Despite these challenges, there is hope for coral reefs. Conservation efforts around the world aim to protect and restore these vital ecosystems. Marine protected areas can reduce local stresses like overfishing and pollution, giving reefs a better chance to withstand the global threat of climate change. Innovative restoration projects are experimenting with growing corals in underwater nurseries and transplanting them to degraded reefs. Some scientists are even breeding corals that are more tolerant of heat and acidity, hoping to help reefs adapt to changing conditions. On a smaller scale, individual actions can make a difference. Choosing sustainable seafood, reducing carbon emissions, and supporting reef-friendly tourism can all help. Even simple measures like using reef-safe sunscreen when swimming or snorkeling can protect the delicate organisms from harmful chemicals. For those lucky enough to visit a coral reef in person, it is hard not to be struck by the sheer energy of the place. The water seems alive with movement, colour, and sound. The snapping of shrimp, the crunching of parrotfish, the distant calls of dolphins. Every nook and cranny hides some new discovery, and the more you look, the more you realise that the reef is not a static structure, but a living, breathing community. These underwater cities have been built over millennia, yet their future depends on choices made in our lifetimes. Protecting coral reefs is not just about saving pretty fish or colourful scenery. It is about preserving one of the most remarkable partnerships in nature and the intricate web of life that it supports. In the great expanse of the ocean, reefs may cover less than 1% of the seafloor, but their impact is vast, sustaining an estimated quarter of all marine species. They are a reminder that in nature, as in cities, the smallest residents can be the most essential, and that the strength of a community, whether above the waves or below them, lies in cooperation. Far from the bustling shallows, coral gardens, and coastal shelter, lies a realm that seems almost empty at first glance. This is the open ocean, a place so vast it covers more than half the planet's surface. Yet in many ways it is a desert. A blue desert where survival depends on movement, adaptation, and a little luck. Here there are no reefs to hide in, no kelp forests to weave through, and no rocks to cling to. Instead, the seascape is defined by distance, depth, and an endless horizon. It is a world of scarcity. Nutrients, the invisible fuel that drives ocean life, are often locked away far below in colder, denser water. The sunlit surface, the epipelagic zone, sparkles invitingly, but for many organisms it offers little in the way of a meal. Only where currents stir the water, bringing nutrients up from the depths, does life flourish in abundance. These upwellings create oases in the blue wilderness, attracting everything from tiny plankton to enormous predators. Outside of these hotspots, survival means constant travel. The inhabitants of the open ocean are built for life on the move. Tuna, for example, are like the greyhounds of the sea, streamlined, muscular, and astonishingly fast. They can cruise for thousands of kilometres, following shifting fronts where warm and cool waters meet, because those are places where plankton blooms attract schools of smaller fish. Bluefin tuna in particular undertake migrations that span entire ocean basins, crossing from one continent to another with the changing seasons. Sharks, too, roam these waters in grand circuits. Some, like the great white, will travel from the coasts of one continent to the shores of another in search of prey. Others, such as the whale shark, the largest fish on Earth, glide slowly through the blue, their enormous mouths filtering plankton and small fish from the water. These gentle giants may journey across entire ocean basins, navigating by cues that scientists are only beginning to understand, perhaps the faint magnetic field of the planet, or subtle changes in water temperature and chemistry. And then there are the great migrants of the marine world. Whales, humpback whales for instance, make one of nature's most extraordinary round trips, travelling from cold feeding grounds near the poles to warm breeding waters in the tropics. They can cover over 8,000 kilometres in a single migration, fasting for months while they make the journey. Blue whales, the largest animals ever to have lived, also roam the open ocean in search of krill-rich waters. In the emptiness of the pelagic world, movement is life, and the great travellers are its masters. Despite the scarcity, the open ocean is not lifeless. Floating in the surface waters are vast quantities of plankton, both phytoplankton, which use sunlight to make energy, and zooplankton, which feed on them. These microscopic drifters form the very foundation of the marine food web. Where plankton is plentiful, fish gather, and where fish gather, predators follow. The ocean's largest creatures, like whale sharks and baleen whales, rely entirely on these tiny organisms for their survival, proof that even the smallest life can support the largest. But the open ocean is not uniform. Within its immensity lie strange and unique places, like the Sargasso Sea. Located in the North Atlantic, it is unlike any other sea because it is defined not by coastlines, but by ocean currents. Bounded by the North Atlantic Gaia, the Sargasso Sea is a floating realm of golden brown seaweed called sargassum. These mats drift on the surface, providing food, shelter and breeding grounds for an array of creatures. Tiny fish hide among the fronds, crabs scuttle over them, and even sea turtles use them as nurseries. For migratory species, the Sargasso Sea is a vital waypoint. American and European eels make an epic journey to spawn here, travelling from rivers and coasts across the Atlantic. Their young then drift on ocean currents for years before making the long journey back to fresh water. The Sargasso is also home to unique animals found nowhere else, creatures perfectly adapted to a floating forest that exists in the middle of an ocean desert. Yet this wilderness, vast though it may be, is not immune to human influence. Fishing fleets crisscross the open ocean, and the sheer emptiness makes it difficult to monitor or manage what happens far from land. Many large migratory fish are overfished, their numbers dwindling despite their long migrations. Plastic pollution carried by currents accumulates in gyres, including the one surrounding the Sargasso, forming patches of floating debris that can trap or be ingested by marine life. Climate change is altering the patterns of currents and upwellings, reshaping the migration routes and feeding grounds that countless species have relied on for millennia. Despite these pressures, the open ocean remains one of the planet's last great frontiers. We have mapped its surface with satellites, yet its depths are still largely unexplored. There are mountain ranges and canyons on the seafloor that no human has ever seen. Even in the surface waters, there are species yet to be described, behaviours yet to be understood, and migrations that remain mysterious. The scale of it all is humbling. A blue wilderness where the horizon seems infinite, and where the creatures that survive do so by mastering the art of movement, endurance, and adaptation. To venture into the open ocean, whether in a ship or simply in the mind's eye, is to step into a world defined by distance. Here, survival means finding food in a place where it can be scarce, navigating without landmarks, and enduring the challenges of storms, predators, and the sheer immensity of the water. And yet for the tuna, the sharks, the whales, and the drifting communities of plankton, it is home. A home without walls, stretching from sunrise to sunset in every direction. Between the sunlit surface and the black abyss lies a realm of mystery, the twilight zone of the ocean, known to scientists as the mesopelagic. This band of water stretches from about 200 metres down to roughly 1,000 metres. a region where sunlight fades to a dim blue glow before disappearing altogether. It is a world of long shadows, perpetual dusk, and some of the strangest life forms on Earth. Here, light is precious. The faint rays that do penetrate are too weak for photosynthesis, meaning no plants or algae grow in this zone. Instead, life depends on food drifting down from above, a constant rain of tiny particles called marine snow. This snow is made of dead plankton, fish scales, bits of fecal matter, and other organic debris. To creatures of the twilight zone, it is as vital as rainfall is to a desert. Every flake carries energy from the sunlit waters above into the deep. Yet, despite the scarcity, the mesopelagic teems with life. One of its most numerous inhabitants is the lanternfish. These small, silver-scaled fish are covered in photophores, tiny organs that produce light through chemical reactions. In the darkness, these spots glow like constellations, sometimes in patterns that help the fish blend into the faint light above, making it harder for predators to spot them from below. Lanternfish are more than just survivors. They're key players in one of the planet's largest animal migrations. Every night, billions of them rise toward the surface to feed on plankton, then return to the depths by daybreak. This daily commute, undertaken by countless species, is the largest movement of biomass on Earth, happening in every ocean and every time zone. Other mesopelagic residents use light for entirely different purposes. The hatchetfish, for instance, has a body shaped like a thin silvery blade, and photophores along its belly. It uses these lights for counter-illumination, matching the faint light above so that its outline disappears against the surface glow. The barrelly fish has perhaps one of the most bizarre adaptations of all, a transparent dome-shaped head that allows it to point its large upward-facing eyes toward the silhouettes of prey above, all while keeping the rest of its body still and hidden. Squid also thrive here, from small darting species to the formidable Humboldt squid, sometimes nicknamed the Red Devil for its flashing colour displays and aggressive behaviour. Many mesopelagic squid can produce light, either to startle predators, signal to mates, or confuse prey. In these dim depths, bioluminescence is more than a party trick. It is a survival tool, as essential as eyesight or camouflage. In fact, it's estimated that over 90% of species in the twilight zone can produce their own light. That light takes many forms. Some creatures emit a steady glow, others flash in bursts or send rippling waves of light along their bodies. Certain deep-sea shrimp, when threatened, release glowing clouds into the water, much like an octopus releasing ink, except this ink glows, momentarily blinding and distracting an attacker. The dragonfish, a predator of the mesopelagic, wields a bioluminescent lure dangling from its chin, waving it like a fishing rod to draw curious prey close enough to snatch. But the twilight zone is not just about light, it is about the absence of it. As you descend through its waters, reds and oranges fade first, swallowed by the blue-green wavelengths that penetrate deeper. Eventually even these vanish, leaving only the faint glimmer of bioluminescent sparks against a darkening backdrop. Eyes in this realm tend to be enormous relative to body size, an adaptation to gather every possible photon. Some animals, like certain squid, have eyes so large they could be mistaken for dinner plates, designed to spot the silhouettes of predators or prey in the faintest shimmer. The environment here poses challenges far beyond the lack of light. Pressures are immense, many times greater than at the surface, and temperatures plunge, often hovering just above freezing. Yet life has found ways to adapt. Muscles and enzymes are tuned to work at cold temperatures, and body structures are flexible enough to withstand the crushing pressure without breaking. Because energy is scarce, many creatures move slowly, conserving every bit of fuel, while others rely on seasonal or nightly feeding frenzies to sustain them for long periods. In this zone, the rules of survival are different. Predators must be opportunistic, feeding on whatever they can find. Prey animals rely on camouflage, deceptive lights, and sudden bursts of speed to escape. Many species are masters of disguise, with bodies that are partially transparent, reflecting the water around them to all but vanish from view. One of the most remarkable aspects of the mesopelagic is its role in the planet's carbon cycle. The nightly vertical migration of fish and other animals from the twilight zone to the surface and back again is not just a hunt for food, it's a massive conveyor of carbon. These creatures feed in the plankton-rich upper waters, then return to the depths, excreting waste and respiring carbon dioxide far below the surface. This process helps lock carbon away in the deep ocean for centuries, playing a crucial role in regulating Earth's climate. For humans, the twilight zone remains largely unexplored. Our submarines and remotely operated vehicles have only glimpsed a fraction of its residents. Nets trawled through these depths bring up an astonishing variety of forms, some delicate and gelatinous, others bristling with spines or trailing long, thread-like appendages. Many of these animals are so fragile that they collapse into unrecognizable shapes once brought to the surface, making in situ observation the only way to truly understand them. There is still much we do not know. How do so many species synchronize their vertical migrations? How do they navigate through what seems like featureless water? What other forms of life might be hiding in this dim realm, their lights never yet seen by human eyes? The mesopelagic holds its secrets tightly, offering only glimpses to those who venture down. And perhaps that is part of its allure. It is a place where darkness dominates, but life has found ways to glow, to signal, and to survive. It is a reminder that even in the most challenging environments, adaptation can create beauty. Flickers of light in an endless dusk, drifting in slow motion far below the reach of the sun. Beneath the twilight zone lies a world so alien that, for most of human history, it was thought to be lifeless. The deep sea begins where sunlight vanishes entirely, plunging into perpetual night at depths of around 1,000 meters and continuing down to the ocean floor, which in some places lies more than 11,000 meters beneath the surface. It is a place where pressure would crush a human submarine without proper reinforcement, temperatures hover just above freezing, and the darkness is absolute. Yet here, in conditions that would seem utterly inhospitable, life has not only survived, but has evolved into forms so strange they defy imagination. The deep ocean floor is far from uniform. Vast stretches of abyssal plains, some of the flattest regions on Earth, extend for thousands of kilometers, their monotony broken only by the occasional undersea mountain or volcanic ridge. These plains are draped in a fine layer of sediment, the slow accumulation of dead plankton, dust, and tiny fragments of shells falling from the upper layers over millions of years. Movement here is glacial in pace. A single grain of sediment may take centuries to settle. The stillness is broken only by the slow crawl of sea cucumbers or the occasional passing of a deep-sea fish adapted to the eternal dark. Then there are the trenches, deep scars in the Earth's crust formed where tectonic plates collide and one is forced beneath the other. The Mariana Trench in the Pacific is the most famous, plunging to nearly 11 kilometers at its deepest point. To put that in perspective, if you were to drop Mount Everest into it, the peak would still be submerged under more than 2 kilometers of water. In these extreme depths, pressures can exceed 1,000 times that of the surface, making survival a feat of extraordinary adaptation. Yet life thrives even here. Microbes cling to rocks, feeding on chemicals that seep from the Earth's crust. Amphipods, small shrimp-like crustaceans, scavenge whatever organic matter drifts down from above. Some fish, such as the snailfish, have been discovered living in trenches far deeper than scientists once thought possible, their bodies lacking the gas-filled swim bladders that would collapse under such pressure. Instead, they rely on flexible bones, special proteins that stabilize their cell structures, and a metabolism tuned to the cold, crushing environment. Among the most remarkable habitats of the deep are hydrothermal vents. underwater hot springs formed when seawater seeps into cracks in the ocean floor near volcanic regions, becomes superheated by magma, and then gushes back into the sea carrying a cocktail of minerals. These vents can spew water at temperatures exceeding 350 degrees Celsius, though the surrounding deep-sea water remains near freezing. Around them, life flourishes in dense, thriving communities. Hydrothermal vents host a unique food chain that does not depend on sunlight at all. Instead of photosynthesis, the base of the food web here relies on chemosynthesis, the process by which bacteria convert chemicals such as hydrogen sulfide into organic matter. These bacteria live freely in the water, coat the rocks in colourful mats, and even reside inside the bodies of larger animals in mutually beneficial relationships. The giant tube worm, a symbol of vent life, has no mouth or stomach. Instead, it houses chemosynthetic bacteria within its body, which produce nutrients in exchange for a safe home. Other vent dwellers include ghostly white crabs, blind shrimp, and deep sea mussels, all part of an ecosystem utterly independent of the sun. Away from vents and trenches, life in the deep sea often seems adapted for both scarcity and surprise. Many fish have enormous mouths and expandable stomachs to swallow prey almost as large as themselves, an insurance policy against long stretches without food. Others, like the anglerfish, use bioluminescent lures to draw in prey in the pitch black. In some species, males are tiny compared to females and permanently attach themselves to their mates, fusing bodies and circulatory systems, an extreme solution to the problem of finding a partner in the vast emptiness. The deep is also home to gelatinous creatures of extraordinary beauty and fragility. Delicate jellyfish drift with long trailing tentacles, some flashing patterns of light in the dark. Comb jellies shimmer with rainbow colours created not by pigments, but by the scattering of light on their moving cilia. Giant siphonophores, colonies of specialised organisms working together as one, can stretch longer than blue whales, hunting with curtains of stinging cells. Temperature plays a decisive role in shaping life here. With no sunlight to warm the waters, temperatures typically remain just a few degrees above freezing. Metabolism slow, movements become more deliberate, and lifespans often stretch far beyond those of shallow water relatives. Some deep-sea corals may live for thousands of years, their slow growth recording environmental changes in their skeletons like ancient tree rings. One of the most striking aspects of the deep sea is its sheer scale. It covers more than half the planet's surface, and yet remains one of the least explored places on Earth. The cost, difficulty, and danger of operating at such depths mean that we have mapped Mars and the Moon in greater detail than our own abyssal plains. Every expedition seems to uncover species never before seen, suggesting that our current understanding barely scratches the surface. The ecological importance of the deep ocean is immense. It acts as a giant carbon sink, storing vast amounts of carbon dioxide and helping to regulate the planet's climate. Many deep-sea organisms play roles in nutrient cycling, breaking down organic material and redistributing it across the seafloor. The health of the deep is intimately tied to the health of the rest of the ocean, even though most surface dwellers will never see it. Human activities are beginning to reach these remote depths. Deep-sea mining for minerals, bottom trawling for fish, and the spread of pollutants threaten habitats that have taken millions of years to form. The slow pace of deep-sea life means that damage can take centuries or longer to heal, making conservation both urgent and challenging. Despite these threats, the deep retains its aura of mystery and wonder. It is a world where the familiar rules of life bend and stretch, where ecosystems thrive in utter darkness, and where evolution has produced solutions so inventive they seem like works of science fiction. The deep sea reminds us that Earth still holds frontiers as alien as any distant planet, vast realms of darkness, pressure, and cold, where life glows, crawls, and drifts in ways that challenge our imagination. The ocean is a realm where size can be pushed to staggering extremes. Nowhere else on Earth do we find animals as massive as those that swim its waters. The sheer buoyancy of the sea allows bodies to grow far beyond what would be possible on land, where gravity constantly works against every ton of muscle and bone. In the ocean, giants can flourish, from whales the size of buildings to sharks that predate the dinosaurs, and even invertebrates so large they stretch our sense of what a mollusk could be. Let us begin with the largest creature ever known to have lived on Earth, the blue whale. Even the biggest dinosaurs of the Jurassic never reached its length. A fully grown blue whale can stretch over 30 metres from nose to tail and weigh upwards of 180 tons. Its heart alone is the size of a small car, and its tongue can weigh as much as an elephant. Despite this monumental size, the blue whale's diet consists almost entirely of krill, tiny shrimp-like crustaceans that it filters from the water using plates of baleen in its mouth. During feeding season, a blue whale can consume several tons of krill a day, engulfing massive mouthfuls of water and then forcing it out through its baleen to trap its prey. This feeding strategy, called lunge feeding, requires a remarkable amount of energy, which the whale replenishes during the summer before migrating to warmer breeding grounds in winter. Blue whales are not the only giants in the whale family. The sperm whale holds the title of the largest toothed predator in the world. With heads that make up a third of their body length, sperm whales can dive to depths of over 2 kilometres in search of giant squid. Their skulls contain a waxy substance called spermaceti, once thought to help them with buoyancy control or echolocation, though its exact function is still debated. These deep diving hunts are feats of endurance, with dives lasting more than an hour before the whale surfaces to breathe. Sharks, too, have their representatives in the Giants Club. The whale shark, despite its fearsome name, is a gentle filter feeder and the largest living fish. It can reach lengths of 18 metres or more and feeds mainly on plankton, small fish and squid. Swimming slowly near the surface with its enormous mouth agape, the whale shark filters thousands of litres of seawater each hour. It roams tropical and warm temperate seas, often covering vast distances in its lifetime. Then there is the basking shark, another giant filter feeder found in cooler waters. It is less massive than the whale shark, but still an imposing sight, with a mouth that can open more than a metre wide. Not all ocean giants are gentle. The great white shark, though much smaller than the whale shark, commands a fearsome reputation as one of the top predators in the sea. Growing to over 6 metres, it is built for bursts of speed and power, with senses finely tuned to detect the faintest whiff of blood in the water from kilometres away. Great whites prey on seals, sea lions, fish, and sometimes even smaller whales, using ambush tactics and a devastating bite. In the invertebrate world, the giant squid and the colossal squid reign supreme. These elusive creatures live in the deep ocean, rarely seen alive by humans. The giant squid can grow to lengths exceeding 13 metres, with eyes the size of dinner plates, an adaptation for detecting faint light in the deep. The colossal squid, found mainly in Antarctic waters, may be shorter but is heavier and armed with rotating hooks on its tentacles, making it a formidable predator in its own right. The battles between these squids and sperm whales have left scars on the whales' heads, a silent testament to encounters between titans in the dark depths. How do such massive creatures survive in the open ocean, where food can be patchily distributed and often far apart? The answer lies in efficiency and specialization. Large marine animals often have slow metabolisms relative to their size, allowing them to go long periods without eating. Many are also migratory, travelling thousands of kilometres to exploit seasonal food abundances. For instance, humpback whales undertake some of the longest migrations of any mammal, moving between nutrient-rich polar feeding grounds in summer and warmer tropical breeding grounds in winter. In the case of filter feeders like the blue whale or whale shark, size is an advantage when consuming enormous quantities of small prey. The larger the animal, the more water it can filter, and the more energy efficient each feeding dive or mouthful becomes. This efficiency helps offset the fact that krill blooms or plankton swarms may only occur in certain regions and seasons. Predatory giants often rely on stealth, endurance, or cooperative hunting to maximize success. Orcas, or killer whales, are the largest members of the dolphin family and exhibit complex hunting behaviors, working together to herd fish into tight balls or to create waves that wash seals off ice floes. Their size allows them to take down large prey, including other whales, while their intelligence enables them to adapt their tactics to different environments. The immense size of these animals also affects their life histories. Many marine giants mature slowly, have long lifespans, and produce relatively few offspring compared to smaller species. This strategy means that populations can take decades to recover from declines caused by human activity. Whaling in the 19th and 20th centuries decimated many whale species, with blue whale numbers reduced to a fraction of their original abundance. Even today, entanglement in fishing gear, ship strikes, and climate-driven changes to food availability remain significant threats. Sharks face their own challenges. Many large shark species are slow to reproduce, with gestation periods that can last over a year and small litter sizes. Overfishing and bycatch have led to steep declines in populations of great whites, basking sharks, and whale sharks in some areas. Squids, while faster growing and shorter lived, are vulnerable to changes in ocean temperature and chemistry that can disrupt their prey and breeding cycles. Despite these pressures, there are signs of resilience. Conservation measures such as protected marine areas, fishing regulations, and bans on commercial whaling have allowed some populations to stabilize or even recover. The sight of a blue whale surfacing, a basking shark gliding through plankton-rich water, or a pod of orcas working in perfect synchrony is a reminder of the ocean's capacity to support life on a truly grand scale. The giants of the sea are more than just marvels of size. They are keystone species shaping the ecosystems around them. Whales help cycle nutrients through the ocean by feeding at depth and releasing waste near the surface, fertilizing plankton that form the base of the marine food web. Sharks help maintain healthy fish populations by preying on the sick and weak, while squid play a crucial role in transferring energy between deep and surface waters. Their survival is intertwined with the health of the entire marine environment. In their presence, there is a sense of humility. These vast creatures have roamed the oceans for millions of years, surviving ice ages, shifting continents, and mass extinctions. They are living links to an ancient, enduring world, one that still holds mysteries far beyond our reach, yet depends on our stewardship to endure. Fish are some of nature's most masterful engineers, the product of hundreds of millions of years of refinement in the most competitive arena imaginable, the open water. The sea is a place where gravity feels lighter, but danger moves in 3 dimensions, where food can be abundant one moment and vanish into the blue the next. Over the ages, fish have evolved bodies that turn them into sleek, efficient and adaptable machines. Whether they're built for darting speed, silent ambush, or slow energy-saving drifting, the designs of fish are as varied as the waters they inhabit. One of their most fundamental adaptations is the streamlined body. Many fish exhibit a fusiform shape, tapered at both ends like a living torpedo, allowing them to slip through water with minimal resistance. This is why predators like tuna, mackerel, and sharks are so fast. Their entire form is tuned to slice through the ocean with minimal drag. Others break the mold entirely, like flatfish that have evolved to live their lives pressed against the seabed, or the laterally flattened bodies of angelfish, perfect for maneuvering through coral mazes. Every curve and contour of a fish's body is a blueprint shaped by the demands of its environment. Beneath their scales lies another key to survival: gills. These remarkable organs are the respiratory engines of the aquatic world, extracting oxygen from water far less oxygen-rich than air. Water flows over delicate gill filaments lined with capillaries, and oxygen diffuses directly into the blood. Fish have evolved a clever countercurrent exchange system. Water flows one way over the gills while blood flows the other, ensuring the most efficient oxygen absorption possible. This is why fish can stay active even in cooler waters where oxygen levels are relatively low. It's a quiet, hidden marvel of design, and without it, the sea would be a far emptier place. Equally ingenious is the swim bladder, a gas-filled organ that acts as a buoyancy control device. By adjusting the amount of gas inside, fish can hover effortlessly at their chosen depth without constantly swimming. This not only saves energy but also allows them to remain still when they need to hide from predators or wait for prey. Some species, like sharks, lack swim bladders and instead rely on constant movement and oil-rich livers to maintain buoyancy, a strategy that keeps them perpetually on the move and often near the top of the food chain. Camouflage is another survival trick in the fish arsenal, and it comes in many forms. Some species are counter-shaded, dark on top and light underneath, making them harder to spot from both above and below. Others can actively change their skin colour thanks to special pigment cells called chromatophores. Reef fish like parrotfish and wrasse use dazzling patterns to confuse predators, while stonefish and scorpionfish resemble the rocks and coral they hide among so perfectly that divers can swim past without ever noticing. In the open ocean, where there is nowhere to hide, transparency is another option. Glassfish and some juvenile fish are almost invisible except for their eyes. For those that rely on speed rather than stealth, the ocean is a racetrack. Species like sailfish and marlin are among the fastest swimmers, capable of short bursts that leave prey with no chance of escape. Their muscles are packed with powerful fibres, and their tails are stiff and crescent-shaped for maximum thrust. On the other hand, endurance swimmers like tuna can cross entire oceans in search of food, relying on a combination of hydrodynamic shape, efficient muscle use, and even warm-bloodedness in some species to keep their muscles primed for action in colder waters. Hunting strategies in fish are as diverse as their habitats. Ambush predators like pike lurk motionless until the perfect moment to strike, while pack hunters such as trevally or jackfish work together to herd smaller fish into tight bait balls before charging in. Some species employ trickery. The anglerfish dangles a bioluminescent lure to tempt prey close enough to swallow whole, while groupers and moray eels have even been observed cooperating, with one flushing prey out of crevices and the other snapping it up. Many fish are also opportunistic feeders, ready to switch diets when their preferred food is scarce. This flexibility can mean the difference between survival and starvation in an environment where conditions can change rapidly due to seasons, migrations, or human activity. Filter feeders like whale sharks and basking sharks simply swim with their mouths open, sieving plankton from the water in vast quantities, while others are specialists targeting only a narrow range of prey. Defense is just as important as offense, and here fish display a whole spectrum of adaptations. Schooling, for instance, is an ancient survival tactic. By swimming in large, synchronized groups, fish can confuse predators with a shifting, glittering wall of bodies. The odds of any one fish being caught drop significantly, and predators may be discouraged from even trying. For more individual approaches, some fish wield venom, such as lionfish and stonefish, whose spines can deliver painful or even dangerous stings. Others use sudden displays of bright colours to startle predators long enough to escape. The sensory world of fish is tuned to detect the slightest changes around them. The lateral line system, a series of fluid-filled canals along their bodies, allows them to sense vibrations and movements in the water. This means they can detect approaching predators, locate schooling companions, or zero in on struggling prey even in murky conditions. Many species also have exceptional vision adapted to their specific environment, from the keen eyesight of reef fish to the low-light sensitivity of deep-water hunters. The adaptability of fish is perhaps best demonstrated by their ability to survive in nearly every aquatic environment on Earth. From the frigid waters beneath polar ice to the scorching heat of shallow tropical lagoons, from the crushing pressures of deep trenches to the fluctuating tides of coastal estuaries, fish have evolved forms and functions to match. They are the living proof that evolution rewards versatility and precision in equal measure. In the grand theatre of the sea, fish are both actors and audience, predator and prey, travellers and homebodies. They are the original test pilots of the ocean's challenges, their designs honed not by human ingenuity, but by the relentless hand of nature over unthinkable spans of time. Every gill, every fin, every pattern of scales tells a story of adaptation, a story that continues to unfold in the ever-changing waters of our planet. In the grand hierarchy of ocean life, the whales get the headlines, the sharks get the reputation, and the dolphins get the fan clubs. But the real rulers of the sea are almost invisible to the naked eye. They drift in endless numbers through every drop of seawater, forming the foundation of the marine food web. These are the plankton, a word that comes from the Greek for drifter, or wanderer. They are not a single species, but a vast, diverse community of organisms united by one trait. They are at the mercy of the currents. Plankton can be split into two broad groups, phytoplankton and zooplankton. Phytoplankton are the plant-like members of the community, though most are actually single-celled algae rather than true plants. They are microscopic, but they are the ocean's equivalent of a rainforest. Endlessly productive, endlessly busy, and crucial to life on Earth. Just like land plants, phytoplankton use sunlight, carbon dioxide, and water to perform photosynthesis. In the process, they release oxygen into the water and eventually into the atmosphere. In fact, it is estimated that phytoplankton are responsible for producing between half and 2/3 of the oxygen in our air. Every other breath you take has a microscopic ocean drifter to thank. Among these sun-powered organisms are diatoms, which encase themselves in intricate shells made of silica, turning their tiny bodies into works of natural art. Dinoflagellates are another group, equipped with whip-like tails to help them move, and some species are even bioluminescent, lighting up the waves at night like spilled starlight. Then there are cyanobacteria, sometimes called blue-green algae, which are among the oldest living things on the planet. These microscopic pioneers were performing photosynthesis billions of years ago, long before the first animals even existed. If phytoplankton are the solar-powered gardeners of the ocean, zooplankton are the grazers and hunters. Zooplankton include a vast array of tiny animals, as well as the larval stages of many larger creatures like crabs, starfish, and even fish. Some, like copepods, are barely bigger than a grain of rice, yet they are among the most abundant animals on Earth. Copepods drift through the water, scooping up phytoplankton like underwater cows munching grass. Others, like krill, gather into enormous swarms so dense they can be seen from space, forming a buffet line for whales, penguins, and seals. The two groups are locked into a constant cycle of life and death. Phytoplankton bloom in the presence of sunlight and nutrients, multiplying rapidly and turning parts of the ocean into green or turquoise swirls visible from satellites. Zooplankton feast on these blooms, which in turn supports the entire chain of predators above them. Without plankton, the ocean's food web would collapse. Even the mightiest blue whale, the largest animal ever to live, depends ultimately on the productivity of organisms so small that millions could fit into a teaspoon. Plankton are also planetary climate engineers. Through photosynthesis, phytoplankton pull carbon dioxide out of the atmosphere, locking it away in their cells. When they die, some of this carbon sinks to the seafloor, where it can remain trapped for hundreds or even thousands of years. This process, called the biological carbon pump, helps regulate Earth's climate. Without it, our atmosphere would hold far more carbon dioxide, and our planet would be a much warmer place. The fate of plankton is tied closely to the chemistry of the water they inhabit. Nutrients like nitrogen, phosphorus, and iron act as fertilizers, boosting phytoplankton growth. But those same nutrients are not evenly distributed across the oceans. areas near coastlines where rivers deliver mineral-rich runoff tend to be highly productive. In contrast, the vast blue deserts of the open ocean can be surprisingly low in nutrients despite all that water. Sometimes entire regions of the sea are limited by a single missing ingredient, such as iron, which can arrive only via dust storms from distant continents. Plankton populations also rise and fall with the seasons. In temperate waters, spring and summer bring sunlight and warmth, sparking massive blooms that support huge increases in marine life. In polar regions, the cycle is even more extreme. Plankton lie dormant through the long, dark winter, then explode into action during the brief summer when the sun never sets. These seasonal surges ripple through the food chain, attracting migrating fish, birds, and mammals to feast on the temporary bounty. Not all plankton are benevolent contributors to the planet's oxygen supply. Some species can form harmful algal blooms, producing toxins that affect fish, shellfish, and even humans. Red tides caused by certain dinoflagellates can turn the sea into a reddish or brownish soup, while releasing chemicals that make shellfish dangerous to eat. These blooms can be triggered by excess nutrients from human activity, such as agricultural runoff, and they are becoming more common in some parts of the world. Yet for all their vulnerabilities, plankton are astonishingly resilient. They have survived ice ages, mass extinctions, and dramatic shifts in ocean chemistry. Still, they are not immune to the changes humanity is bringing about. Rising ocean temperatures can disrupt the delicate timing of plankton blooms, separating them from the migrations of the animals that depend on them. Ocean acidification, caused by the absorption of excess carbon dioxide, can affect species like diatoms and coccolithophores that build shells or skeletons from calcium carbonate. The loss of these species would ripple outward, affecting everything from tiny zooplankton grazers to massive filter-feeding whales. Plankton are also beautiful in ways that defy their scale. Under a microscope, diatoms reveal glass-like shells etched with patterns more intricate than any cathedral window. Radiolarians, another planktonic group, grow spiny, symmetrical skeletons that look like alien sculptures. At night in certain parts of the world, bioluminescent plankton turn the surf into glowing blue foam, a reminder that the ocean is never truly dark. It is tempting to overlook these microscopic drifters in favour of the ocean's giants, but the truth is that the giants are only possible because of them. Plankton are the invisible majority of life in the sea, the base upon which everything else is built. They sustain the oxygen in the air, draw down the carbon from the sky, and feed the chain of life from the tiniest krill to the most immense whales. Every mouthful of air you breathe, every fish that swims in the sea, and every ecosystem that depends on the ocean owes something to this teeming, drifting multitude. Though you may never see them in person, they are there, riding the currents, blooming in sunlight, and quietly keeping the planet alive. Beneath the shifting surface of the ocean lies a world as dramatic and varied as any mountain range or desert on land, a hidden landscape that covers more than 2/3 of our planet, yet remains largely unexplored. The seafloor is not the flat, featureless plain that early cartographers once imagined. Instead, it is a realm of towering peaks, plunging canyons, and vast ridges that stretch for thousands of miles, shaped by forces both ancient and ongoing. Let us start with seamounts, underwater mountains that rise from the seafloor, often the remnants of extinct volcanoes. Some seamounts are solitary giants. Others form long chains that trace the movement of tectonic plates over volcanic hotspots. These peaks can be taller than Mount Everest when measured from base to summit, yet many never break the surface. Despite being submerged, they are biodiversity magnets, interrupting currents and drawing nutrient-rich water upward, creating oases of life in the open ocean. Coral gardens, sponge fields, and schools of fish thrive along their slopes, and migratory species like tuna and sharks often treat them as refueling stations during long journeys. Then there are the submarine canyons, deep, steep-sided valleys that cut into the continental shelves and slopes. Some, like the Grand Canyon of the Bering Sea or the Jemtchug Canyon, dwarf even the most famous canyons on land. These underwater gorges are carved by ancient rivers during times of lower sea levels, as well as by the persistent action of turbidity currents, dense flows of sediment-laden water that can rush down the slopes faster than a human can sprint. Canyons funnel nutrients and organic matter from the coast to the deep sea, feeding communities that live far below the reach of sunlight. Stretching across the globe like the seams on a baseball is the mid-ocean ridge system, the longest mountain range on Earth. Formed where tectonic plates are pulling apart, these ridges are sites of continuous geological activity. Molten rock wells up from the mantle, creating new oceanic crust and slowly pushing the plates apart. The Mid-Atlantic Ridge, for example, runs for about 10,000 miles from the Arctic to the Southern Ocean, dividing the Atlantic in two. Along its length, underwater volcanoes erupt in darkness, building new seafloor and sometimes even creating islands. Volcanoes beneath the waves are not just confined to mid-ocean ridges, they can also appear at subduction zones, where one tectonic plate is forced beneath another, or at hotspots, plumes of magma rising from deep within the earth. When they erupt, the spectacle is hidden from human eyes, but the results can be immense. Some underwater eruptions release towering plumes of ash and pumice, while others unleash lava flows that cool rapidly into bizarre bulbous shapes called pillow lavas. In certain cases, volcanic islands are born, only to be eroded by waves and wind over centuries, leaving behind the isolated peaks we call seamounts. Scattered across the abyssal plains, those seemingly endless flat stretches of the deep sea floor are deposits of minerals and metals that could one day tempt human industry. Manganese nodules, for instance, are small, rock-like concretions rich in manganese, iron, nickel, copper and cobalt. They form incredibly slowly, often growing just a few millimeters every million years as minerals precipitate from seawater and coat tiny fragments of shell or rock. Hydrothermal vent fields, meanwhile, are mineral treasure troves. When seawater seeps into cracks in the crust near volcanic activity, it heats up, becomes enriched with metals, and then gushes back into the ocean through chimney-like structures. As the hot fluid meets the cold seawater, the metals precipitate, forming deposits of copper, zinc, gold, and even rare elements. Hydrothermal vents are more than just mineral factories, they're also cradles of unique ecosystems. In the complete absence of sunlight, life here depends on chemosynthesis, a process where bacteria harness the energy from chemical reactions, such as the oxidation of hydrogen sulfide, to produce organic matter. Towering tube worms, ghostly white crabs, and blind shrimp thrive in this alien world, entirely independent of the sun. Scientists studying these environments often remark on how they may mirror conditions on early Earth, and could even provide clues about the potential for life on other worlds. The topography of the seafloor is in constant flux, reshaped over millions of years by the slow but relentless movement of tectonic plates. Earthquakes beneath the ocean can trigger submarine landslides, sending cascades of sediment tumbling into the depths and altering the contours of the seabed in an instant. Over longer timescales, the opening and closing of ocean basins have transformed the face of the planet, rearranging continents and creating entirely new marine landscapes. Yet for all we have mapped, vast portions of the deep sea floor remain a mystery. Modern sonar mapping and remotely operated vehicles have revealed extraordinary details of certain regions, but large swathes of the ocean remain charted only in the vaguest outlines. In many places, our maps of Mars are more precise than our maps of the seabed beneath our own planet. This hidden terrain is home to countless undiscovered species, unknown mineral formations, and geological features that could reshape our understanding of Earth's history. The seafloor is also a keeper of records. Sediment cores drilled from its layers hold a detailed archive of past climates, ocean chemistry, and even mass extinction events. Fossilized microorganisms, chemical traces and mineral patterns locked away in these sediments allow scientists to reconstruct Earth's environmental story, sometimes stretching back tens of millions of years. These archives tell of ice ages and warm periods, of asteroid impacts and volcanic cataclysms, and of how life in the ocean responded to these upheavals. For centuries, humans saw the ocean's depths as unreachable, a place of permanent mystery. Today, we have the tools to venture into this shadowy realm, though our exploration has barely scratched the surface. The seafloor is not a static, lifeless expanse. It is a dynamic, ever-changing world, rich with drama and surprise. Beneath the waves, mountains rise, valleys plunge, volcanoes erupt, and life thrives in forms that challenge our imagination. The Earth's hidden landscape is as varied and awe-inspiring as anything above the waterline, perhaps even more so, for it remains a place where mystery still outweighs knowledge. Far below the sunlit waves, in a realm where light cannot reach, life persists, and not just persists, but thrives in ways that challenge our understanding of biology. These deep-sea ecosystems do not rely on the familiar chain of photosynthesis that dominates the surface world. Instead, they are powered by chemistry, tapping into the Earth's internal energy rather than the sun's radiant heat. At the heart of this phenomenon are hydrothermal vents, cracks in the seafloor where seawater seeps into the crust, heats up from contact with underlying magma, and gushes back into the ocean loaded with minerals and chemicals. The vent fluids can be hotter than the boiling point of water at the surface, yet they remain liquid under the crushing pressure of the deep ocean. When this superheated, mineral-rich water hits the cold seawater, metals and sulfides precipitate out, forming towering chimneys known as black smokers, or, in some cases, lighter-coloured white smokers. Around these vents, life has found a foothold in one of the most extreme environments on the planet. The primary producers here are chemosynthetic bacteria and archaea, microbes capable of using chemicals like hydrogen sulfide or methane as an energy source to manufacture organic compounds. Instead of chlorophyll, they rely on enzymes that can capture the energy from chemical reactions. This makes them the base of a food web that is entirely independent of sunlight, a remarkable example of life finding a way where it was once thought impossible. These microbes don't just drift in the water. Many live in close partnerships with larger organisms. The most iconic of these are the giant tube worms, which can grow taller than a human. Lacking mouths, stomachs, or digestive systems, these worms instead house dense colonies of chemosynthetic bacteria within a specialized organ called a trophosome. The worm draws in sulfide-rich water through its plume, and the bacteria inside convert those chemicals into food. In return, the worm provides the bacteria with a safe, stable environment. It is a symbiosis as intimate and vital as any coral-algae relationship in shallow seas. Other creatures have adapted equally inventive strategies. Certain deep-sea clams and mussels host chemosynthetic bacteria in their gills, while yeti crabs cultivate bacterial mats on their hairy claws, farming their own food. Shrimp near vents have adapted light-sensing organs on their backs to detect the faint thermal glow of vent openings, guiding them to these oases in the darkness. Even predatory species like vent crabs and deep-sea fish rely indirectly on chemosynthetic life, feeding on herbivores or scavenging organic matter that originates from the microbes. The food webs in these regions are strikingly compact compared to those in sunlit ecosystems. Energy is produced at the microbial level and passed quickly to the larger inhabitants, with minimal waste. But this efficiency is balanced by vulnerability. Vent ecosystems depend entirely on the continued flow of chemicals. If a vent cools or becomes blocked, the life around it can collapse in a matter of months. For mobile species, the solution is migration to another vent field, but for sessile organisms like tube worms, extinction is often inevitable. Hydrothermal vents are not the only places where life without sunlight thrives. Cold seeps, areas where hydrocarbons like methane seep out of the seabed, also host chemosynthetic communities. The process here is slower and less dramatic than at vents, with gentle streams of gas rather than superheated plumes of minerals. Still, the chemical energy supports dense populations of mussels, tube worms and bacteria, often forming long-lived ecosystems that can persist for centuries. Brine pools, where hypersaline water collects in depressions on the seafloor, create yet another bizarre niche. The dense, salty water is so heavy it forms a distinct layer within the ocean, and it can be toxic to most marine life, except, of course, to the specialised communities that have adapted to its chemistry. The evolutionary significance of these ecosystems cannot be overstated. Many scientists believe that life on Earth may have begun in environments much like hydrothermal vents, where a constant supply of chemical energy and mineral surfaces could have catalysed the formation of complex organic molecules. The vent's combination of heat, minerals, and chemistry offers a plausible cradle for the earliest microbes, billions of years before the first sunlight-based photosynthesizers appeared. Studying these modern chemosynthetic communities is like peering back into the deep past, glimpsing the possible origins of life itself. They also hold implications for the search for extraterrestrial life. Moons like Europa and Enceladus have subsurface oceans in contact with rocky mantles, creating conditions that could mimic Earth's hydrothermal vents. If life can exist without sunlight here, feeding entirely on chemical reactions, then it could potentially exist beneath the icy crusts of distant worlds. The organisms clustered around vents on our own planet may be the closest analogues we have to alien life forms. These deep ecosystems are not isolated curiosities. They are also linked to the broader ocean through the dispersal of larvae and organic matter. When vent organisms spawn, their larvae drift with the currents, sometimes settling far from their birthplace if they happen upon a suitable new vent. This connectivity means that vents, despite being scattered and transient, can form a loose network across ocean basins. But it also means they are vulnerable to disruption. Damage to one site can ripple outward through the population dynamics of others. In recent decades, human activity has begun to encroach on these hidden worlds. Deep-sea mining operations are eyeing the mineral-rich chimneys for their valuable metals, while trawling and other fishing practices can inadvertently damage fragile vent and seep habitats. Because these ecosystems are slow to recover, even small disturbances can have long-lasting effects. Conservation efforts, including marine protected areas and international agreements, are being proposed and in some cases enacted to shield these remarkable places from harm. In the dark heart of the ocean, where sunlight has never shone, life has carved out a living through chemistry alone. From towering tube worms to microscopic bacteria, every inhabitant of these realms is a testament to nature's adaptability and ingenuity. They remind us that life's story is not just written in green leaves and golden rays, but also in the invisible reactions of molecules deep within the Earth's crust. Here, at the meeting point of rock, water, and heat, the boundaries of what is possible are constantly redrawn, and the result is one of the most extraordinary spectacles our planet has to offer. The oceans are not just vast blue backdrops to the drama of life on Earth. They are also one of the most important systems regulating our planet's climate. Without them, our world would swing wildly between scorching heat and bitter cold, and life as we know it would be hard-pressed to survive. Acting as both a giant heat sink and a massive carbon vault, the oceans help keep Earth's temperature within a range where life can flourish. One of the most crucial roles the oceans play is absorbing heat from the sun. Water has a high specific heat capacity, meaning it can absorb and store large amounts of thermal energy without changing temperature quickly. This makes the oceans the planet's thermal stabilizers. When the sun beats down on the equator, the ocean's surface soaks up and stores the heat, slowly releasing it over time. This process prevents the land from heating too fast during the day and cooling too quickly at night. It also smooths out seasonal changes, making summers less blistering and winters less frigid, especially for coastal regions. But the oceans do not just store heat passively. They move it around the planet in a complex system of currents. Warm surface water from the tropics travels poleward, while colder, denser water sinks and flows toward the equator in the deep ocean. This great conveyor belt of heat transport helps prevent the equator from becoming unbearably hot, and the poles from turning into lifeless ice deserts. Regions like Western Europe, for instance, enjoy much milder winters than their latitude would suggest, thanks to the warmth delivered by currents like the Gulf Stream. Alongside heat regulation, the oceans are the largest active carbon sink on the planet, drawing carbon dioxide from the atmosphere. This happens in two main ways. The first is physical. Carbon dioxide dissolves into the surface waters, especially in cooler regions where gas solubility is higher. Once there, it can be mixed downward by currents and stored for decades or even centuries in the deep ocean. The second method is biological. Tiny photosynthetic organisms, phytoplankton, absorb carbon dioxide during photosynthesis. When they die, some of this carbon sinks to the ocean floor in the form of organic material, locking it away from the atmosphere for hundreds to thousands of years. This biological pump is a quiet but powerful force, keeping our atmosphere from building up dangerous levels of greenhouse gases. However, the balance is delicate. As humans release more carbon dioxide through burning fossil fuels, the oceans have stepped up their absorption. But this has a side effect: ocean acidification. When carbon dioxide dissolves in seawater, it forms carbonic acid, lowering the pH of the water. Even small shifts in acidity can have big impacts on marine life, especially creatures that build shells or skeletons from calcium carbonate, like corals, oysters, and certain plankton. If the ocean's ability to store carbon becomes compromised, the planet's climate regulation system could falter. Another way the oceans influence climate is through powerful large-scale climate patterns like El Niño and La Niña. These are not storms, but shifts in the normal behaviour of the tropical Pacific Ocean and its interaction with the atmosphere, and they can ripple through the entire globe's weather systems. Under normal conditions in the equatorial Pacific, trade winds blow steadily from east to west, pushing warm surface water toward Asia. This piles up a deep layer of warm water in the western Pacific and allows colder, nutrient-rich water to upwell along the coast of South America. This normal state is called La Niña when it's slightly stronger than average. Cooler water in the eastern Pacific and intensified trade winds. La Niña years tend to bring wetter conditions to places like Australia and Southeast Asia, while the western coasts of the Americas can see drier weather. El Niño flips this pattern. The trade winds weaken or even reverse, allowing the warm water to slosh back eastward across the Pacific. The upwelling of cool water off South America is suppressed, meaning the eastern Pacific becomes unusually warm. This shift changes where heat is released into the atmosphere, altering weather patterns worldwide. El Niño years can bring torrential rains and flooding to parts of the Americas, drought to Australia and Indonesia, and even changes in the tracks of hurricanes and the severity of winters in far-off regions. Both El Niño and La Niña are part of what scientists call the El Niño Southern Oscillation, a natural cycle, though there is evidence that climate change may be influencing its behaviour and intensity. The effects of these oscillations go far beyond weather. Fisheries can collapse when nutrient-rich upwelling stops during an El Niño, as plankton populations crash without their usual supply of deep ocean nutrients. Agricultural production can be devastated when rainfall patterns shift suddenly. Public health can be affected too, as floods increase the spread of waterborne diseases in some areas, while droughts reduce access to clean water in others. The oceans also regulate climate through their role in the water cycle. Evaporation from the sea surface provides most of the moisture in the atmosphere, which later falls as rain or snow. This is especially important in the tropics, where warm waters fuel towering thunderstorms that help drive the global circulation of air. Storm systems like hurricanes draw their power from warm ocean waters, and the intensity and frequency of these events can shift as ocean temperatures change. In recent decades, scientists have become increasingly aware that the oceans are warming overall due to human-driven climate change. Much of the excess heat trapped by greenhouse gases, over 90%, has gone into the oceans. This stored heat is not harmless. It can intensify storms, accelerate the melting of polar ice, and disrupt ecosystems from coral reefs to the open sea. Warmer waters expand, contributing to sea level rise that threatens coastal communities. Yet despite these challenges, the oceans remain our planet's most reliable climate buffer. They have shielded humanity from the full force of our own emissions for decades, buying us time. But this buffering capacity is not infinite. As the oceans warm, their ability to absorb both heat and carbon dioxide changes, potentially creating feedback loops that could speed up climate change. Understanding and protecting the oceans is therefore not just about preserving marine life. It is about safeguarding the stability of the entire Earth system. From the quiet depths where carbon is stored for centuries, to the roaring Pacific where El Niño can rearrange global weather, the oceans are the planet's beating heart of climate regulation. They have shaped the conditions in which civilizations have risen, crops have grown, and ecosystems have flourished. In their vast, swirling waters lies both the memory of past climates and the key to our future stability. To watch over the oceans is, in a very real sense, to watch over ourselves. For as long as humans have been able to dream of what lies beyond the horizon, the sea has been both a barrier and a pathway. It is the great connective tissue of our planet, carrying goods, ideas, and people across distances that would otherwise take months or years to traverse. Long before the first written records, people were taking to the water in rafts, dugout canoes, and reed boats, using nothing but muscle power, intuition, and the position of the sun and stars to guide them. Navigation began in its most basic form, keeping a coastline in sight and following it to new hunting grounds or trading partners. Over time, this evolved into more daring ventures offshore. Ancient Polynesians were among the most remarkable early navigators, crossing thousands of kilometers of open ocean in double-hulled canoes, guided by the patterns of the waves, the flight of seabirds, and the positions of the stars. Without compasses or charts, they reached and settled islands scattered across the vast Pacific, creating one of the most extraordinary feats of exploration in human history. In the Mediterranean, civilizations like the Phoenicians, Greeks, and Romans built their wealth and power through mastery of the sea. The Phoenicians, in particular, became known as the traders of the ancient world, venturing beyond the Strait of Gibraltar, and possibly even reaching the British Isles in search of tin. They developed sturdy ships and sophisticated navigation methods, including the use of the North Star as a reliable guide. The Greeks expanded maritime trade routes across the Aegean and beyond, while the Romans used their naval might to control the Mediterranean, which they proudly called Mare Nostrum, our sea. The development of more accurate navigation tools was a turning point. The magnetic compass, first used in China over 1,000 years ago, eventually spread to the Islamic world and Europe, revolutionizing long-distance sea travel. Mariners could now navigate even when the sky was overcast or the coastline invisible. The astrolabe, and later the sextant, allowed sailors to measure the angle between the horizon and a celestial body, letting them determine their latitude with far greater accuracy. The age of exploration in the 15th and 16th centuries transformed the relationship between humanity and the oceans. Figures like Christopher Columbus, Vasco da Gama, and Ferdinand Magellan undertook voyages that connected continents in ways that had never been seen before. Trade networks expanded to a global scale, with goods such as spices, silk, gold, and silver flowing across the seas. But this age was also marked by darker currents. Colonization, the transatlantic slave trade, and the exploitation of indigenous peoples were all carried on the same ships that brought new goods and ideas. Fishing has been at the heart of human interaction with the sea since prehistory. ancient coastal communities relied heavily on the ocean for sustenance, developing ingenious methods to harvest its bounty. The Norse were skilled cod fishermen, drying and preserving their catch to last through the winter. In Japan, entire cultural traditions grew around fishing, from the delicate art of preparing sashimi to the communal labour of hauling in nets. In the Arctic, Inuit peoples hunted seals, whales and fish, relying on deep knowledge of animal behaviour and seasonal migrations. Fishing cultures have often developed unique boat designs perfectly suited to their environments. The slender, graceful dhows of the Arabian Sea harnessed the seasonal monsoon winds to carry traders and fishermen alike. The sturdy longboats of the Vikings could navigate both open seas and shallow rivers, enabling raids and trade across Europe. In Southeast Asia, outrigger canoes provided stability in choppy waters, allowing fishers to venture far from shore. The sea has also been an inexhaustible source of myth and legend. For ancient mariners, the ocean's unpredictability and vastness inspired stories of gods, monsters, and enchanted lands. The Greeks imagined Poseidon, god of the sea, wielding his trident to stir up storms. Norse sagas spoke of the Midgard serpent, a creature so large it encircled the world. Sailors' tales brimmed with krakens, mermaids and ghost ships, part warning, part entertainment, and perhaps a way to explain the unexplainable in a world where a sudden squall could spell disaster. Many myths served a practical purpose. Stories of dangerous shoals or treacherous currents were wrapped in supernatural warning to make them memorable. A mythical sea monster lurking in a certain stretch of water might actually be a coded message about hidden reefs. Likewise, tales of islands that appeared and disappeared could be linked to real volcanic eruptions or shifting sandbars. Maritime culture also shaped music, art, and literature. Sea shanties kept the rhythm of labour on deck, helping crews work in unison while lifting sails or hauling ropes. Artists captured the majesty and terror of the sea, from serene harbour scenes to furious storms tossing ships like toys. Writers used the ocean as a metaphor for freedom, danger, and the unknown, whether in Homer's Odyssey, Coleridge's The Rime of the Ancient Mariner, or Melville's Moby Dick. Trade over the seas has always been about more than goods. It has been about the exchange of ideas. Languages borrowed words from seafaring neighbours. Religions spread along maritime trade routes, from Buddhism carried by sailors across the South China Sea to Islam, spreading along the Indian Ocean's bustling ports. Technologies like shipbuilding techniques, navigational charts, and even agricultural crops were shared and adapted through oceanic contact. The industrial era brought new changes. Steamships replaced sails, reducing dependence on the wind and cutting journey times dramatically. The opening of canals like the Suez and Panama further shrank the world, allowing ships to bypass long and hazardous routes. Global shipping became the backbone of international commerce, a role it still holds today. Yet even in this era of massive container ships and satellite-guided navigation, the romance and peril of the sea remain. The relationship between humanity and the sea has never been static. It has evolved from a source of food and a boundary to be feared to a superhighway for global trade and a stage for cultural exchange. Yet for all our mastery of navigation and shipbuilding, the sea still demands respect. Its power can humble even the most advanced vessels, and its mysteries continue to challenge human understanding. The sea has shaped our history in ways both visible and invisible. It has been the route by which empires expanded, goods were exchanged, and cultures met. It has fed billions, inspired generations, and carried both dreams and nightmares across its waves. For humanity, the ocean has never been merely a backdrop. It has been a central character in our shared story, as unpredictable and enduring as the tides themselves. The sea has always seemed too vast to harm, a boundless expanse where rivers disappear, storms dissipate, and life flourishes in abundance. For centuries people treated it as an infinite provider and an endless dumping ground. But the reality is becoming impossible to ignore. The ocean is in trouble. The threats it faces are no longer isolated or slow-moving. They are converging, accelerating, and reshaping the marine world in ways that could alter life on Earth itself. One of the most visible and insidious problems is pollution. Every year, millions of tons of plastic enter the ocean. Some of it is easy to spot. Discarded fishing nets drifting like ghostly traps, bottles bobbing along the shore, grocery bags tangled in seaweed. But the more dangerous threat is invisible. Microplastics, tiny fragments from degraded waste, synthetic clothing fibres, and industrial processes. These particles are now found everywhere, from the surface waters to the deepest trenches, and even inside marine animals. Fish ingest them while feeding, seabirds mistake them for food, and tiny plankton can become coated with microscopic debris. The chain of contamination moves up through the food web, ultimately reaching our own dinner plates. Chemical pollution adds another layer of harm. Agricultural runoff carries nitrogen and phosphorus into coastal waters, feeding explosive algae blooms. When these blooms die off, they decompose in a way that consumes oxygen, creating dead zones where few creatures can survive. Industrial waste, heavy metals like mercury, and oil spills all add toxic burdens to marine life. Even substances meant to help, like certain anti-fouling paints for ships, can leach harmful compounds into the sea. Overfishing is another crisis, one that strips the ocean of its living wealth. For centuries, fishing seemed an inexhaustible source of protein and income, but modern industrial techniques, massive trawlers, long lines stretching for kilometres, sonar to locate schools, have pushed many species to the brink. Iconic fish like Atlantic cod, once so plentiful they were said to walk on each other's backs, have collapsed in certain regions. Bluefin tuna, prized for sushi, are caught faster than they can reproduce. Sharks, hunted for their fins and caught as bycatch, have seen populations crash by more than 90% in some areas. This isn't just about losing individual species. Removing top predators like sharks disrupts entire food webs. Small fish may boom in numbers, overgrazing plankton or seagrass beds, which in turn affects other creatures. The balance that evolved over millions of years can unravel quickly when one link in the chain is broken. As if these pressures weren't enough, the chemistry of the ocean itself is changing. When humans burn fossil fuels, a significant portion of the resulting carbon dioxide dissolves into seawater. This triggers a process called ocean acidification, lowering the pH and making the water more corrosive to organisms that build shells or skeletons from calcium carbonate. Corals, oysters, clams, and certain plankton struggle to grow in these conditions. For coral reefs, already stressed by pollution and overfishing, acidification adds yet another blow, weakening their very foundations. The ocean is also warming, absorbing more than 90% of the excess heat trapped by greenhouse gases. This rise in temperature is not uniform. Some regions are heating much faster than others, but the effects are widespread. Warm water holds less oxygen, creating hypoxic zones that suffocate marine life. Many species are shifting their ranges toward cooler waters, disrupting established ecosystems and affecting the communities that depend on them. For creatures like coral, even small spikes in temperature can trigger bleaching events, where they expel the algae that provide them with energy, turning ghostly white and, if stress persists, dying. The warming ocean also fuels stronger storms, changes rainfall patterns, and disrupts currents that regulate climate. Melting polar ice adds fresh water to the sea, which can alter salinity and potentially slow major circulation systems like the Atlantic meridional overturning circulation. Such changes could have far-reaching consequences for weather, agriculture, and biodiversity worldwide. All of this leads to a loss of marine biodiversity at a pace scientists find deeply concerning. Species are vanishing before they can even be studied, taking with them unique genetic adaptations and ecological roles. Coral reefs, kelp forests, and mangroves, habitats that shelter countless species, are being degraded or destroyed. In some places, shifting baselines mean younger generations grow up never knowing the abundance their grandparents once saw. Yet for all the damage, the ocean still holds remarkable resilience. Some fish populations rebound when given a chance, as seen in marine protected areas where fishing is restricted. Coral species with higher heat tolerance are being studied to help restore reefs. Efforts to reduce single-use plastics, improve wastewater treatment, and create sustainable fisheries are gaining traction. International agreements like the High Seas Treaty aim to safeguard biodiversity beyond national borders. The crisis is urgent, but not hopeless. The ocean's health is tied to our own. Its currents moderate our climate, its organisms provide food and oxygen, its beauty and mystery inspire art, science, and wonder. Protecting it means addressing pollution at its source, rethinking how we harvest its resources, and tackling climate change with genuine commitment. It is a sobering truth that the damage done over decades will not vanish overnight. But it is equally true that the ocean has an extraordinary capacity to heal if given the opportunity. Mangrove forests can regrow, seagrass beds can return, fish stocks can replenish. Each step toward restoration is an investment not just in marine life, but in the stability and livability of the planet we all share. The story of the sea is not yet written to its conclusion. Whether it becomes a tale of decline or recovery will depend on choices made in our time, choices about energy, consumption, conservation, and respect for the vast living world beneath the waves. The ocean is not infinite, it is precious, it is fragile, and it is still, for now, alive with possibility. The ocean may be under strain, but it is not beyond saving. In fact, despite the scale of the challenges, there are stories of hope, examples where determined action, innovation, and patience have led to remarkable recoveries. The sea, when given a chance, can heal itself in ways that seem almost miraculous. One of the clearest success stories comes from the creation of marine protected areas, or MPAs. These are sections of the ocean set aside to limit or completely prohibit activities like fishing, drilling, and mining. The idea is simple: protect habitats long enough for life to rebound, and the benefits will ripple outward. In places like the Great Barrier Reef Marine Park in Australia, or the Papahanaumokuakea Marine National Monument in Hawaii, restrictions have allowed fish populations to flourish and coral cover to increase. Even heavily overfished species can make surprising comebacks when given a safe space. These protections work not only because they shield wildlife directly, but because they allow entire ecosystems to function as they should. A reef with a healthy population of large predators like groupers or reef sharks is a different, more balanced place than one stripped of its top species. Seagrass beds thrive when herbivorous fish keep algae in check, and mangrove roots become nurseries for countless juveniles. The benefits often extend beyond the boundaries of the protected zones, as fish and other organisms spread into surrounding waters. Some of the most inspiring turnarounds have happened in places where local communities are directly involved in conservation. In Fiji, for example, villages have revived traditional taboo areas, where fishing is temporarily banned to allow stocks to replenish. These closures are often respected because they are rooted in cultural heritage, and when they are lifted after a set period, the harvest is richer than before. Similar community-led approaches in the Philippines and East Africa have transformed struggling coastal fisheries into sustainable ones. Restoration projects have also shown promise. Seagrass meadows, mangroves, and salt marshes, habitats once seen as expendable, are now recognised as vital for both biodiversity and climate resilience. They store large amounts of carbon, filter pollutants, and buffer shorelines from storms. In Virginia, the largest seagrass restoration project in the world began by simply scattering seeds into suitable habitat. Over 2 decades, it has grown into thousands of hectares of thriving meadow, attracting scallops, crabs, and fish, and locking away significant amounts of carbon each year. Coral reefs, notoriously sensitive to heat stress and pollution, are proving more resilient than many had feared. Some corals naturally withstand higher temperatures, and scientists are working to breed and transplant these hardier varieties into struggling reefs. Projects in the Caribbean, the Pacific, and the Indian Ocean are experimenting with coral gardening, where fragments are grown in underwater nurseries before being replanted. While these efforts alone cannot stop bleaching caused by climate change, they can help buy time and preserve genetic diversity until global temperatures stabilise. Technological innovation is also playing a role in ocean healing. Advances in satellite monitoring allow researchers to track illegal fishing vessels in real time, shining a light on activities that once happened in the shadows. Drones and underwater robots can survey fragile habitats without disturbing them, mapping coral reefs and deep-sea vents in unprecedented detail. Artificial reefs, made from eco-friendly materials, are being deployed to provide shelter for marine life and reduce pressure on natural reefs. In the fight against pollution, creative solutions are emerging. Biodegradable alternatives to plastic are gaining ground, while some ports are installing sea bins that skim floating debris from the water's surface. In certain rivers, barriers catch waste before it can drift into the open sea. Even more ambitious are large-scale cleanup projects like the effort to remove plastic from the Great Pacific Garbage Patch, using long floating booms to gather debris for recycling. While cleanup alone will never solve the plastic problem, it sends a powerful message about responsibility and action. Addressing climate change, the biggest long-term threat to ocean health, requires reducing greenhouse gas emissions, but the ocean itself can help in that fight if restored. Protecting and expanding blue carbon ecosystems like mangroves, seagrasses, and salt marshes could lock away vast amounts of carbon while providing shelter for wildlife. Some researchers are exploring more experimental methods, like encouraging the growth of certain plankton species that naturally absorb carbon dioxide, or enhancing the alkalinity of seawater to increase its carbon storage capacity. Cultural shifts are also part of the solution. Sustainable seafood certifications give consumers a way to support responsible fishing, while awareness campaigns highlight the connection between what happens on land and the health of the sea. Education plays a critical role here. When people understand that their choices have real impacts, from what they eat to how they dispose of waste, they are more likely to act with care. The recovery of certain species offers proof that these combined efforts can work. Humpback whale populations, once devastated by commercial whaling, have rebounded in many parts of the world after hunting bans were enforced. Green turtle numbers are rising in areas where nesting beaches are protected. Even species like the northern elephant seal, reduced to a few dozen individuals a century ago, now number in the hundreds of thousands thanks to legal protection and dedicated conservation. Of course, ocean recovery is not quick or easy. It requires patience measured in decades, not months. Coral reefs may take years to rebuild, fish stocks can be slow to recover, and reversing the effects of pollution is an ongoing struggle. But the ocean's track record of resilience offers reason for optimism. Life beneath the waves has endured mass extinctions, ice ages, and dramatic shifts in sea level. It is adaptable, but only if given the space and conditions to adapt. The most powerful part of the healing process may be the way it multiplies its benefits. A healthy reef does not just support fish, it supports tourism, coastal protection, and cultural heritage. Restored mangroves shelter communities from storms while providing breeding grounds for commercially important species. Cleaner, more abundant seas create a feedback loop of health, stability, and opportunity for both marine life and people. While the threats to the ocean are real and urgent, they are not insurmountable. Each restored habitat, each protected zone, each innovative solution chips away at the damage and builds a foundation for renewal. The ocean has given humanity immeasurable gifts: food, oxygen, trade routes, inspiration. Ensuring its future health is not just an act of environmental stewardship, but a commitment to our own survival and well-being. And perhaps that is the most encouraging truth of all. The ocean is not asking for miracles. It is asking for space, respect, and the chance to do what it has always done: thrive. When we meet it halfway, the rewards are immense and the possibilities stretch as far as the horizon. Looking ahead, the ocean's future is as vast and unpredictable as the waters themselves. It holds both warnings and promises, scenarios in which humanity either adapts alongside a changing sea or suffers from failing to heed its messages. Climate change will be one of the defining forces shaping what happens next, not only to the ocean, but to life on land as well. If greenhouse gas emissions continue at their current pace, ocean temperatures will keep rising, ice sheets will retreat, and sea levels will climb higher than at any time in recorded history. This warming is not uniform. Some regions will heat more quickly than others, altering currents that have been stable for millennia. The Gulf Stream, for example, already shows signs of slowing, and its disruption could change weather patterns across Europe, Africa, and the Americas. Tropical storms may become more intense, polar seas less icy, and the once reliable rhythm of seasonal upwelling, where nutrient-rich deep waters feed surface ecosystems, may falter. The chemistry of the ocean will also shift. As it absorbs more carbon dioxide, its waters grow more acidic, affecting species that build shells or skeletons from calcium carbonate. Coral reefs, oysters, clams, and many plankton species will struggle to maintain their structures in such conditions. This ripple effect could impact food chains from the microscopic level up to top predators. Yet, the degree of these changes depends heavily on the choices humanity makes today. Strong climate action could limit acidification, preserve more of the ocean's biodiversity, and keep the most extreme warming scenarios at bay. Sea level rise is another reality that will shape our relationship with the ocean in the decades to come. Even in moderate climate projections, many low-lying island nations face the loss of habitable land, while coastal cities will contend with frequent flooding. Engineering solutions like seawalls, restored wetlands, and floating architecture may buy time, but they will not work everywhere. In some regions, communities may have to retreat inland, reshaping cultures and economies that have been tied to the shoreline for centuries, yet it is not all a story of loss. The ocean is also a frontier of incredible potential, especially as technology makes deeper and more remote exploration possible. To date, humans have mapped less than a quarter of the seafloor in detail, and we have physically visited only a tiny fraction of the deep ocean. Autonomous submersibles can now dive for months at a time, gathering high-resolution images, geological data, and even samples from places no human has ever been. These expeditions often overturn our assumptions. Hydrothermal vents, once thought barren, teem with complex ecosystems that rely on chemosynthesis instead of sunlight. Deep trenches reveal creatures adapted to pressures and darkness so extreme they seem alien. Even the midwater, the vast shadowy space between surface and seafloor, continues to surprise scientists with new species and strange behaviours. The more we explore, the clearer it becomes that the ocean is not a static landscape but a living, shifting world still full of mysteries. The resources of the deep sea are another subject of growing attention, though not without controversy. Vast fields of polymetallic nodules, containing cobalt, nickel, and rare earth elements critical for renewable energy technology, lie scattered across abyssal plains. Extracting them could accelerate the transition to a low-carbon economy, but it risks damaging fragile ecosystems that take centuries or millennia to recover. Balancing technological progress with environmental protection will be one of the defining challenges of this century. Marine biotechnology may hold equally transformative possibilities. Organisms living in extreme ocean environments often produce unique enzymes, proteins, and chemical compounds. These could inspire new medicines, biodegradable materials, or industrial processes that work in ways current technology cannot match. For example, heat-resistant enzymes from deep-sea microbes are already used in certain manufacturing processes, while bioluminescent proteins from jellyfish have revolutionized medical imaging. Protecting biodiversity is not just about saving species. It may be about safeguarding the keys to future innovation. The ocean's role in regulating climate makes it central to humanity's own survival. It absorbs around a quarter of the carbon dioxide emitted by human activities each year, and more than 90% of the excess heat trapped by greenhouse gases. Without this buffering effect, the planet would already be far hotter and less hospitable. However, this service has limits. Warming waters can hold less oxygen, leading to expanding dead zones where marine life cannot survive. Protecting the ocean's capacity to act as a climate stabilizer means tackling both global emissions and local stresses, like pollution and overfishing. Renewable energy from the sea could also help steer us toward a more sustainable future. Offshore wind farms are growing rapidly, wave and tidal energy projects are in development, and floating solar installations are beginning to appear in calm waters. These technologies promise to deliver clean energy while reducing reliance on fossil fuels, though they will need careful planning to avoid harming marine habitats. In imagining the ocean's future, it's important to remember that human and ocean destinies are inseparable. A collapse of fisheries would not just be an environmental tragedy, it would threaten the food security of billions. Rising seas will not simply redraw coastlines, they will alter economies, migration patterns, and geopolitical stability. Conversely, a thriving ocean can act as a foundation for resilience, providing resources, regulating climate, and supporting cultures that have lived in harmony with the sea for generations. Perhaps the greatest unknown is how quickly we can adapt our own behaviour. The pace of change in the ocean is accelerating, but so too is our ability to monitor, understand, and respond. Real-time data from satellites, sensors, and autonomous drones now allows scientists to track currents, storms, and ecological changes across the globe. Public awareness of ocean issues has never been higher, and international agreements, while imperfect, are moving towards stronger protections for high seas biodiversity. The next 100 years could see the ocean enter a period of unprecedented stress, or one of remarkable recovery. Which path it takes will depend largely on the priorities we set today. We can choose to see the ocean as a limitless storehouse to be exploited until it is empty, or as a partner in the long-term survival of our species, a partner that needs space, protection, and respect. The ocean's future is not an abstract problem for later generations. It is unfolding now in every decision about energy, pollution, conservation, and exploration. Its vastness may make it seem eternal, but it is sensitive to the smallest shifts in balance. And in that balance lies our own future, because the ocean does not simply border our world, it sustains it. The fate of the seas and the fate of humanity are, and always will be, the same story. The sea has always been more than water. It is a mirror reflecting back our history, our curiosity, our fears, and our hopes. It has shaped the rise and fall of civilizations, carried our ships to new worlds, and fed us when the land could not. In its depths, it hides the beginnings of life itself, and in its restless surface, it reminds us that change is inevitable. From the first tidal pools where simple molecules came together, to the vast modern oceans where whales sing and plankton drift, the sea is the thread that connects the story of Earth to the story of us. We have been explorers of its edges for thousands of years, and yet we still know so little about it. We can name the highest peaks on the moon, but we have not mapped most of our own seafloor. We can follow the path of a comet across the solar system, but the migrations of countless marine creatures remain partly a mystery. The ocean holds secrets that no human eye has yet seen, and perhaps never will. But the possibility is always there, pulling at our imagination like the tug of a gentle tide. In its rhythm, the sea offers a kind of wisdom. Tides move in and out with quiet inevitability, waves break and reform, currents flow endlessly in great loops. The ocean does not hurry, but it never stops. It is patient, resilient, and endlessly adaptive. In its persistence, there is a lesson for us. a reminder that life can endure if it can change. Yet the ocean is not invulnerable. We have poured our waste into it, taken from it without limits, and warmed it with our excess heat. We have seen coral reefs bleach, fish stocks collapse, and coastlines erode. These are warnings, not prophecies. They are evidence that our relationship with the sea must change if it is to remain a source of life and wonder for generations to come. But there is also reason for hope. The ocean has an astonishing ability to recover when given the chance. Protected marine reserves have seen fish populations rebound within a few short years. Pollution controls have brought cleaner waters to harbours that were once choked with waste. Whale populations, once driven to the brink, are slowly increasing again in many regions. Nature is not fragile. It is resilient if we give it space to breathe. This resilience is not an invitation to complacency. It is a call to action, grounded in the knowledge that what we do now matters. The ocean's health is not separate from our own. It regulates our climate, feeds our people, and gives us the oxygen in every second breath we take. The same waves that carry beauty and inspiration carry the very systems that make life possible. To harm the sea is to harm ourselves. Stewardship of the ocean is not only a scientific or political challenge, it is also a deeply human one. It asks us to see beyond the horizon of our own lifetimes, to imagine the seas our grandchildren will inherit. Will they stand on the shore and see reefs blooming with life? Or will they look out over a silent, empty expanse? Will they marvel at the sight of a breaching whale, or read about such creatures in history books as we do with the dodo? The answers will depend on how we choose to live now, on whether we treat the ocean as an infinite resource or as a partner in survival. And perhaps that partnership is the truest way to think of it. The ocean is not ours to own. It is a living system in which we participate. We are part of its vast web, not separate from it. The rain that falls on our crops began as water lifted from its surface. The minerals in our bodies were carried here through ancient seas. The heartbeat of the planet is, in many ways, the heartbeat of the ocean. When you stand at the edge of the shore, you can feel it, that quiet pull between yourself and the water, the salt on the wind, the endless horizon, the sound of waves folding into one another. It is both grounding and infinite. It makes you feel small, yet connected to something vast. That feeling is not an illusion. It is the truth. The ocean is the oldest thing we have ever known, and it will be here long after we're gone. But in the time we share with it, we can choose to be caretakers rather than conquerors. The sea asks for no monuments, no recognition. It asks only that we give it the chance to continue its timeless work, sustaining life, shaping the planet, and offering refuge to the wild and the wondrous. If we protect it, we are protecting ourselves. And so, the future of the ocean rests not in distant possibility but in present choice. It is written in the laws we pass, the waste we prevent, the energy we use, the knowledge we share. It is shaped by the respect we teach to our children when they first feel the tide lapping at their feet. Close your eyes and imagine the sea not as it is today, but as it could be. Clear waters shimmering with schools of fish, coral gardens glowing beneath the surface, the songs of whales echoing through the deep. Imagine standing at the shoreline not with worry but with wonder. The tide pulls in, the tide pulls out, the waves keep coming, and in their endless, soothing rhythm, the ocean whispers that it is ready to heal, if only we let it.